This is supposed to be about black holes. The title which I gave tentatively is Physics at the Horizon, Mind the Cap or Mind the Gap. I use the font such that you cannot tell the difference between them. My name is Iosif Bena. I'm from IPHT, which is a lab in France in the Atomic Energy Commission. And this is supposed to be a black hole with a jet coming out from the middle of an accretion disk. So why do you study black holes? This is stuff which is quite generic. You guys probably don't need such introductions, but it's important to remember. They exist in nature. We can find them in binary systems, and they have about between 1 and 30 solar masses. And also you can find them in the centers of galaxies, and they have between 1 billion and 66 billion solar masses. And in particular, one of them was recently captured in a photo using a very complicated machinery using the Event Horizon Telescope. That's the black hole in the middle of the M87 galaxy. The mass is 6.5 billion solar masses, so it's a mega big, huge black hole. Moreover, they emit gravitational waves. So this is the picture of two black holes merging and distorting the space-time and emitting gravitational waves. And recently we had LIGO and Virgo measuring such waves, and moreover there will be more things coming up. But the main reason for which I study black holes is because they take quantum mechanics and general relativity, which are the two building blocks of all the physics, and they put it in a very sharp contrast. And I want to explain you where this contrast is coming from. In general relativity, black holes are very easy to obtain. They are produced by gravitational collapse. You take a ball of dust or a ball of water or a ball of anything, you let it collapse under the effect of gravity, and they are formed. Black holes have a singularity, they have a horizon, and the horizon is the place through which if you cross you can never come back. Moreover, the horizon is a surface which is null, and therefore if you throw something through it you can actually never get back. And the easiest and essentially the information thrown into the black hole is lost. That's what general relativity tells you. So essentially, if you form a black hole, the only things which characterize it are the mass, the angular momentum, and the charge. You cannot form configurations where the black hole has some extra stuff around, sticking out of it, and so on and so forth. This is called black hole hair. Such things cannot be formed. There are theorems by people who do, hardcore math, proving these things. And John Wheeler had this famous saying, "Black holes have no hair." Essentially, you cannot form such configurations, and it's impossible to distinguish again between a black hole which is formed by the collapse of matter, or antimatter, or elephants, or bureaucrats, or whatever you want. Black holes, again, they lose all the information of what came forming them. You can see I live in France, so therefore you see how I choose my things. In the US, people use grass students, which I always find horrible. But bureaucrats, it goes. So if you want to see this in equations, we have the black hole. There's the Schwarzschild black hole, which is the simplest black hole of them all. Is described by a metric, which again has a term dt squared. There's a minus sign here, and there's a place here which is the horizon, where this quantity becomes 0, and the physics of this black hole, I'm not going to get into it too much, is explained by this Penrose diagram, which essentially gives you the physics in a nutshell. And the horizon, you see, is the surface which is null, where the light goes. If you are a real particle, going in a normal massive particle, you travel, time is flowing and you move a bit. But everybody traveling slower than the speed of light moves inside this light cone. And nobody can go outside of the light cone. Nobody can go because it would mean going faster than the speed of light, and you're not supposed to do that. And therefore, once you cross a horizon, you see that once you cross a horizon, you are doomed to hit the singularity. If you want to get out, you have to go faster than the speed of light, which is impossible. So this is again in a nutshell how black holes are seen in general relativity. Now, in quantum mechanics, on the other hand, physics is always reversible. Physics is described by a wave function, and there's a Hamiltonian. The Hamiltonian is Hermitian, and therefore the evolution of psi is unitary. Whatever you do, you can also undo. Quantum mechanics says all physics is reversible, and information is never lost. Now, if you describe black holes in quantum mechanics, you can associate to black holes a temperature and an entropy. You can actually show that the physics of black holes, once you put quantum mechanics in, is a physics which is very, very similar to thermodynamics, just to normal room temperature, air in the room thermodynamics. And in particular, the equations found by Bekenstein and Hawking ages ago are that the entropy of the black hole is given by the area in Planck units. And that's, again, the Planck unit is very small, the areas can be quite large. And the temperature of the black hole is given by this formula, essentially the mass of the sun divided by the mass of the black hole times this number, 10 to the minus 8 kelvins. You can actually put the temperature into, real units. Now, if you look at the black holes which you have around, if you take, for example, a black hole which has the same mass as the sun, that black hole would have an entropy which is over 10 to the power 77. That's a huge number. If you look at the black hole in the middle of the Milky Way, which is called the Sagittarius A star, that black hole has an entropy which is 10 to the power 90. That's a bit more. Still, those are huge numbers. The black hole which we have captured in a picture using the Event Horizon Telescope in the middle of M87 has an entropy which is 10 to the power 96. And the biggest possible black hole which is known to mankind, which is the one in the TON 618 quasar, that one actually has a mass which is 10 to the power 98. That's basically an entropy which is 10 to the power 98. So this is the entropy of the black hole. Now, what Bekenstein and Hawking have shown is that black holes are thermodynamic objects. Essentially they obey various equations. The entropy, for example, always increases in physical processes, and so on and so forth. So this is something which you can actually establish. Essentially, the second course, when you take the first course in general relativity, you learn about the equations and stuff. At the second course, with the second semester of general relativity, people do this kind of equations. They show that the entropy of the energy of the black hole changes. And you have first law of thermodynamics, second law of thermodynamics, and so on and so forth. This is what we know about black holes. Now the problem is that if you look at the black holes let's take this, the biggest path as black hole known to mankind, the one in the middle of this quasar called TON 618. That one has an entropy which is 10 to the power 98. According to quantum mechanics. And this number 10 to the power 98 is a quantum number because you have the classical area divided in units of the Planck length. So there's a quantum. So h bar is there. This is a quantum effect. This is a quantum result. You had a question, or I keep on? So essentially, if you look at this black hole, quantum mechanics tells you that it has e to the power 10 to the power 98 states. That's a lot of states. E to the 10, and you put 98 zeros here, and that's how many states this black hole has. This is what quantum mechanics tells you. And again, this is established by all this work by Hawking and Bekenstein. This is actually established. It's an established piece of physics. On the other hand, if you look in general relativity says that for a given mass, charge, and angular momentum, there's a single solution. It's just one big fat solution, and therefore there's only one state. And this conflict between quantum mechanics and general relativity, between 10 to the power e to the 10 to the 98 and 1, this is again the biggest number of physics which is unexplained. Now, starting from this number, you can formulate the information paradox, you can form this, you can form that. There are many paradoxes and inconsistencies which you can find, but the root of all these things comes from this difference. The fact that in quantum mechanics, black holes are supposed to have e to the 10 to the 98 states, so again a huge number of states, and in general relativity, there are uniqueness theorems which don't allow anybody, anything except, any hair, except, the one and only black hole solution. And therefore, in general relativity, we have one state, and in quantum mechanics, you have, again, e to the 10 to the 98 states. That's again the biggest number in physics. Now, how can we explain it? How can we find the states? In Texas language, where is them black hole states? Where can you find these black hole states? How do they look? What's going on? How do you get this e to the 10 to the 98 states? Where are they? To do that, you have to use a quantum gravity theory. You really have to, work hard, and you have to compose a quantum gravity theory. I'm a string theorist. I'll be giving you the string theory approach to those things. But I'll have side remarks about other approaches, as time goes by. Now, in string theory, what one does, string theory is a theory in 10 dimensions, very complicated, using various membranes and strings and branes. I'm not going to go into that. That's not the purpose of this class. But what one can do, one can actually put together many of these branes in various ways, and you can actually construct objects which look like a black hole, which have the same charge as a black hole. And there's a simpler question, which is, can one actually count how many stringy objects can I build using, again, the strings and branes in a regime of parameters where gravity is not very important, and I can do string theory, and can I actually understand the entropy of the black hole, not here when I have the horizon, but in some other regime of parameters. Can I actually get this number, e to the 10 to the 98? You know, this is a huge number, and can I get this number in any other way? And the simplest black hole is a very simple black hole, and I think we can understand very easily how the entropy gets counted. It's a black hole which is formed in string theory by taking some D1 branes, which are just strings, and some D5 branes, which are some membranes which have 5 dimensions, in 10 dimensions. Everything happens in 10 dimensions, but for the purpose of this talk, you can actually ignore the 4 extra dimensions of the D5 branes, and then you put momentum on them. So you have a D1 brane on a circle. It's a string wrapping a circle, and then you put a D5 brane, which you can also think of as a string wrapping a circle. Now, if you put one D1 brane, one string, on a circle of radius r, then it's very simple, just quantum mechanics, that the momentum of this string is actually quantized. Again, when you have a circle of radius r, the momentum quanta come in units of 1 over r. You can put 1 over r, 2 over r, 3 over r, 4 over r. You cannot put momenta which have 47.7 over r. This is quantum mechanics. Now, if you have multiple d branes, instead of having one d brane on this circle, you have multiple d branes. Let's suppose you have n1 d1 branes. Then you have two options. You can either have the d1 branes separate, meaning you just have them disjoint, or you can actually wrap them into one big fat d1 brane, which comes back to itself. Now, if you put the momentum on this object, you see that the length of this guy is not anymore 2 pi times r, but it's actually 2 pi times n1 times r. And therefore, the momentum quanta on this d1 brane wrapped n1 times, it's no longer 1 over r, but actually becomes 1 over n1 times r. So your momentum quanta became much, much lighter. Normally a quantum has a 1 over r. Now the quanta became 1 over n1 times r. Now, this is what's happening if you put a single type of d branes. If you put two types of d branes, you can put d1 branes, which I'm putting here in red, and you put n1 of them, and then you put d5 branes, and you put n5 of them. String theory has, again, strings, and they have these d branes which are objects where the strings end. Now, a string is a line which can go between one d brane and the other. And if you take, in this particular case, one string which I have here in green, which is stretching between this d brane and this d brane, you can ask how many times does this thing have to go around before coming back to itself. If the numbers n1 and n5 are coprime, if they are equal, of course, you only have to go n1 times. But if the numbers are coprime, you can show that, again, let's say this is 7, this is 5. You go 5 times on this guy, you are back at the same place, but here you're not at the same place, you're here. Then you go 5 times again, and you are some other place, you go 5 times again, and you can show very easily that you have to go around n1 times and 5 times before you come back to the same place as where you were before. And therefore, the mass gap of the system of, again, n1 d1s and n5 d5s, which are coprime, but that's for the purpose of this lecture. You don't need to worry about that too much. The mass gap of the system is actually equal to 1 over n1 times n5 times r. So you see that the system, because you put some d branes together, all of a sudden it got some excitations which are very cheap. It's very easy to make one excitation. You just have to use this tiny amount of energy. Now, when you have a total momentum on a d brane, let's say you have a total momentum of the system, which is np. And therefore, there are basically np over r is the total number of momentum quanta available is np, and the amount of momentum is np divided by r, carried by quanta which have the size 1 over n1 and 5 times r. How many quanta do you have in the system? The answer is n1 times n5 times np. And how many states do you have in the system? The number of states gives you the number of partitions of this. Essentially, how do you partition this number, n1 and 5 times p, into integers? Because again, you can put the momentum, you can put, so let's take the example when n1 times n5 times np is 2. Okay, n1 is 1, n5 is 1, and np is 2. Then you can do two things. You can put one quanta of energy 2, this is this guy, or you can put two quanta of energy 1. That's the partition. So the partitions of the number 2 are only 2. when you have n1 times n5 times np equals to 5, some bigger number, how many partitions do you have? Well, you can put 5 quanta of energy 1, you can put 3 quanta of energy 1 and 1 quantum of energy 2. You can put 1 quantum of energy 1, 2 quanta of energy 1 and 1 quantum of energy 2. Again, those are all partitions. And you can also put 1 quantum of energy 1 and 1 of energy 4. You can put 1 of energy 1, 2 of energy 2. And you can actually find very easily, you know, all the possibilities. Now the question is, what's happening if n1 times n5 times np is mega big and large? So, you know, let's say the number is, you know, 10 gazillions. How many quanta do you have? How many partitions do you have? And that's a question which you can actually try to work out. If you like math, it can be done. Essentially, you have to think about the polynomial 1 plus x squared plus x to the all the way to infinity, multiplied by 1 plus x squared plus x to the 4th plus x to the 6th plus and so on, multiplied times 1 plus x cubed x to the 6th and so on. And you basically take all the polynomials which have powers of x, which are again jumping in powers of 1, and 2, and 3, and 4, and 5, all the way to infinity. And you look at the coefficient of the term of order x to some power, and it's a calculation which can be done. Again, it's something which people who do a bit of math and, you know, who do string theory counting, they're supposed to know how to do. During my PhD, I didn't know how to do that. During my postdoc, I didn't know how to do that. I only learned how to do that, you know, when I got a faculty position, you know, a few years ago, not long time ago. So, you know, it's not an easy thing, but, you know, it's a fun thing. If you're a math kind of person and you want to ask the question, how many partitions do I have of a certain number when the number is very large? How does the number of partition grows? It's a cool math question. The answer is that for large n1, n5, np, the number of partitions is equal to e to the power s, where s is a number which is equal to 2 pi times n1 times n5 times np, again times this total number, divided by 6 under the square root. That's the answer. Again, you do all this calculation and so on. Now, this number is not the entropy of the black hole. Why is it not the entropy of the black hole? I told you that we are counting the strings, but the strings are not a single kind of strings, because again you have this D1 D5 system. And you know, you can do a bit of string theory. It's not very complicated to show that on the D1 D5 system there are actually 4 possible orientations of this open string. This open string can have 4 possible polarizations in space-time, and therefore when you count, it's not, this is the number for one single orientation, but because once you realize that you actually have 4 different species of quanta, then you actually have to show that, and moreover, all these 4 different species of quanta have fermionic partners. Counting bosons is one thing. You know, if you put bosons in a box, how many quanta can you put? Counting fermions is more complicated. You know, you see, if you count fermions, for example, you're not supposed to count this, you're not supposed to count this, you're not supposed to count this, because, you know, you cannot put 2 fermions in the same state. So when you count fermions, the partition of n1 and 5 times np with fermions are only this guy, and this guy. So fermions are much more nasty to count. You know, they have much less states. But you can show that when you have fermions, one can also do the calculation. And at the end of the day, once you take into account that you have bosons, you have fermions, you have 4 types of boson, 4 types of fermions, the final number you get is actually 2 pi times n1 and 5 np to the power 1/2. This is how many configurations of strings and branes you can put with these particular charges. Again, e to the power this animal. That's what the calculation, this is again the number of string and brane configurations you can build. Now, how do you find the black hole entropy? The black hole entropy, I told you that is given by the area in units of L Planck, and the black hole metric in 5 dimensions is given by this beautiful formula. The formula is actually very easy, because the horizon is always when GTT equals to 0. GTT equals to 0, if you look here, is where this power, where this guy blows up. Because when this guy blows up, this is a minus 2/3, so this goes to, so GTT goes to 0. So the horizon is at r equals to 0. And you can actually calculate very easy the area of the event horizon at r equals to 0. And you find that the area, which is divided in units of L Planck square with a factor of 4, is equal to, again, this number, 2 pi n1 and 5 np to the power 1/2. And this is the calculation which has been done by Strominger and Waffa back in '96, and since then there are gazillions of people working on these kind of things. The thing which is quite shocking is that on one hand you have a black hole solution, you calculate an area in a classical solution, and you find some entropy. And the other calculation is, you take a bunch of strings and branes. I told you, you look at these partitions and you find the same entropy. And that's something which, again, is quite remarkable. And when you have more complicated black holes, this is not just a simple polynomial. This equation becomes a horrible nightmarish thing. You can have modular forms, you can have hypergeometric functions, you can have modular forms. The most disgusting things you can think about in math, I don't think there's any object in math which is nasty enough, which has not been done, which doesn't appear here. I mean, it's such a complicated area that, personally, I want to stay as far away as possible away from it. Yes, you had a question.
So what is RP?
RP is basically, so the point is, the charges of this black hole, Q1, Q5, and QP, are linked with these numbers, R1, R5, and RP. But there's a relation which is a bit more complicated. I didn't show it. I had it on a previous version of the slides, but I didn't want to show it. So when you have a solution, the number of the 1 branes determines this number, this R1. The number of the 5 branes determines this number, R5. And the number of momentum quanta determines this number, RP.
Of the string that is between the two branes.
Yes, it determines the total momentum. So when you have when you have a system, the system has a momentum. The momentum of the system appears in the solution as again through this number RP. Now the momentum, which you measure at infinity, once you go inside, you notice that this momentum is actually carried by these tiny fractional guys. So you have 10 quanta of momentum, but if your n1 and 5 is a million, you actually have 10 million microquanta which live on this system, and it's this 10 million microquanta which actually give you the entropy. But at infinity, the momentum you measure is 10. You only have 10 units of momentum on this circle, but the momentum is actually carried by these very tiny fractionated carriers. And this is called, and this phenomenon is called fractionation. So again, ugly objects. And the point is, again, you count quantum states at 0 gravity on one side, you count a classical black hole horizon area, you do two very different calculations, and the two things match. And it's not numbers matching numbers, it's actually functions matching functions. And again, a function has an infinite number of Fourier components if you think about decomposing it. So therefore, when two functions match, it's actually an infinite set of numbers which match. This is not just one number equal to one number. This is an infinite set of numbers equals to another infinite set of numbers. So you can see that there's something there. There's some deep connection there. There's another way to understand it. Those of you who know ADS-CFT, who have done holography, who know a bit about the ADS-CFT correspondence. In the ADS-CFT correspondence, you have a boundary which has some states. And there's a bulk dual, which is called the ADS bulk, which has a black hole. And what this connection shows is that essentially the number of states of the CFT is equal to the entropy of the black hole. There's another way to see this connection, which was realized actually a few years after Strominger and Waffa did this matching. So this is the story about the black holes. This is again the story of the state of the art of the physics back, 96 and a few years after. So this is ancient.
Sorry, but what do you mean by zero gravity?
Sorry?
What do you mean?
When I compute these strings matching around here, when I compute these partitions, I'm ignoring the interaction between these momentum quanta. You see, when you have a system and you have two momentum waves, when gravity is strong, the momentum gives you some metric, and the other momentum gives you some metric, and the two momentum waves start interacting with each other. Gravitational interaction. Here I'm turning off. I'm just counting, momentum waves, ignoring their interaction. So I'm working in the regime of parameters where gravity is not important. I can think about dialing my coupling constant, and I dial my coupling constant to make gravity to be 0 or to be irrelevant for this particular system. Then I go to the other regime of parameters when the black hole exists, and then I make my gravity strong. And once I make my gravity strong, I notice that I actually have a black hole solution. So in this regime of parameters, my momenta have interacted, my d1s have interacted, my d5s have interacted, they have backreacted, they have given me this horrible messy solution, which again takes a while to find. I mean, this is a horrible supergravity solution, That's complicated, a bit more messy than the Schwarzschild black hole. So in this regime of parameters, my brains have back reacted, the interactions are strong, gravity is strong, all the gravitation dynamics is turned on. In the other regime, the gravitation dynamics is turned off. And in a sense, the matching is done between one regime of parameters, where I can do calculations where gravity is not important, and the other regime of gravity is important. Now the question is, what's happening? So this is the matching, and again, you see this, you have this bunch of strings and branes in one regime of parameters, and you go to the black hole regime of parameters where gravity is important, and you get the black hole solution. The question which one can ask, the second question which one can ask is, what's happening if I don't think about computing the entropy, but I just take one particular state of this Strominger-Vafa ensemble. So instead of looking at all the possible states and counting partitions of N1 and 5 MP, I want to look at one particular state, the one which has 1, 17, 35, 29, some particular distribution, one particular quantum of my system, which is one state of my system. And the question is, what's happening if I take one particular state? Now, if I take one particular state, there are two possibilities. One possibility, which has been believed for many, many years, is that this particular state, when you go to the regime of parameters where the black hole exists, becomes something which is identical to the black hole. It gets a horizon and it becomes a big fat object with a horizon. However, what we have been finding over the past 15 years, my collaborators and I have been finding that actually many of these states, maybe not all, just huge number of them, instead of getting a horizon and looking like this, they actually look different. They look very different. They actually look exactly, they become some solutions which look exactly like the black hole. They have the same asymptotics, they have the same throat region, but instead of having a horizon, they actually have a cap. They have a region where space-time ends. It's exactly like a bag. Essentially you go down to the bottom of the bag and you come out. The black hole is not like a bag. A black hole, once you cross in the horizon, you go there and you're lost forever. You cannot come back. These geometries, these particular geometries, you go in and then you scatter and you come out. And what we have been finding is that some of these Strominger-Vafa states, they actually become this kind of configurations. And the big questions which many people have been asking themselves over this period, which was actually stirred by my tour in 2003, is it possible that the microstates, the pure states which give you the entropy of the black hole, instead of having a horizon, they're actually these kind of solutions which don't have a horizon. None of them has a horizon. They're all capped solutions. And somehow the black hole solution would be a thermodynamic description of an ensemble of these horizonless configurations. That's basically the question which people have been asking. Is it possible that maybe things are like this? So in a sense, all the pure states of the black hole, all the microstates of the black hole correspond to these solutions. And then you have the black hole solution, which gives you some thermodynamic ensemble average of the physics, but doesn't give you the real microscopic physics. And people actually have been arguing, and again, if you want to solve this conflict which I told you before between general relativity and quantum mechanics, that the only way to solve it is if something like this happens. That's basically what has been arguing using information theory. I'm not going to go into that direction, but there are arguments which use information theory that if you want to solve the conflict between quantum mechanics and GR, you have to have such a picture of this form or some similar form. Now, there's another way to see this picture, again, in the language of ADS-CFT. Again, you have this boundary theory where gravity is not important, and you have states and you have an ensemble of the states. Now, on the bulk, in the dual ADS theory, where you have a non-trivial, where gravity is strong, you have a black hole solution, and you have, again, these configurations which have no horizon. And somehow what we are trying to show is that all the states of the system correspond to these horizonless configurations, and the black hole just gives you the ensemble description, the ensemble description of the physics. And again, this is not some idea which is hand waving and so on. This is something which one can actually establish in string theory. One can actually prove it by constructing such animals. Now, let me give an analogy. To understand this analogy, what's the difference between the black hole and the microstate geometries thereof? You have to think of the best way to think about this is about the air in this room. If you look at the air in the room, there are two ways of describing the air. You can describe the air as a perfect fluid, as an ideal fluid. PV equals nRT, D equals TdS plus PdV. you know, if you want to fly an airplane, for example, if you take a paper airplane and you want to study the motion of the paper airplane, that's a very good description. You can do it, and you know, it's enough. You don't need to know more. This thermodynamic description is the effective theory of the air for sizes which are, you know, big enough. However, we know that the air is not a perfect fluid. The air is a bunch of molecules which zoom around at, like, you know, 200 and something kilometers an hour back and forth and hit us all the time, and you know, they fill up this room, and you know, they go chaotically and bump into each other and bump into us and bump into the walls. This is what the air is. The air is not a perfect fluid. The fluid is a description of the physics. But the real microscopic description of the air is actually as a bunch of molecules, which can be typical, like the one we have in the room right now. It's also possible that at some point all the molecules in this room decide to go to that corner, and the rest of the room becomes vacuum and we all die. It would be headlines in the newspapers tomorrow. It's very unlikely, you know, it's much more likely that the newspaper will go bankrupt tomorrow, or, you know, some moon is going to fall on the earth. You know, there are many things which are more likely, but you know, it can happen. All the molecules in the air could go to this corner. They can become very atypical, and then, you know, we would be in a very atypical state. But most of the states of the system are typical. How can we find that the air is made of molecules? Does anybody remember the history of physics? How did people realize that the air is made of molecules? It was Boltzmann who actually realized, and you know, there are basically experiments. For example, this Brownian motion, which was found by this drop experiment by Millikan. Essentially, he dropped a tiny droplet of oil, and then, you know, you see that this oil actually gets moved around, and you know, there's an electric field, and you know, it moves in the electric field, so you can see that the charge is quantized, and you can also see the motion of this droplet because the air is hitting it from all directions. This Brownian motion is actually really what's telling you that the air is not made of a fluid. The air is really a bunch of molecules going around. Same, and you know, you have other phenomena which are even more interesting, like, you know, Bose-Einstein condensation. If you want to make liquid air, for example, you know, things like that. Those are not visible. Those are phenomena which are not visible in this description. What we're trying to show is that for the black hole, the same thing happens. The solution which you find in the textbook, the nice, beautiful Schwarzschild solution, the one you find in the textbooks, which you study and you learn and so on. That solution is a thermodynamic solution, which is good at large distances. If you want to do gravitational lensing, of course, you're more than welcome. But if you want to do physics at the horizon, and in particular if you want to describe information loss, and maybe even gravity waves, you actually have to use this kind of objects, the ones which I was showing you around, the ones which don't have a horizon. This is basically the difference. Exactly like for the air, the molecules of the black hole are given by these horizonless configurations. This is actually what we're trying to what we're trying to show. This is actually this is the direction in which, you know, the research line goes. Now, the problem is, again, so what are we saying? We are saying that at the horizon of the black hole, essentially, there's something there. There's a structure. There's a microstructure which replaces the horizon. And when you go to the horizon, you'll actually be bumping into this microstructure. And again, when you look at this black hole solution, you know, this is the horizon. You see here, this is the black hole, and this is the horizon. And you know, we're basically saying that, you know, here be microstructure. The way in the old maps, you know, people had these ancient maps, and then, you know, they said some places saying, you know, here be dragons. And the same way, you know, we're saying that, you know, here be microstructure, you know, right at this particular location. Now, people have been actually saying that, you know, one should put structure at the horizon from a long time. Again, we have this information paradox. We have this big discrepancy between quantum mechanics and GR. The easiest way of solving it would be just to argue that maybe there's something at the horizon which captures all the information of the black hole, which captures all the physics of the black hole, which captures all the entropy of the black hole, and we don't need a black hole. People have been arguing this for many years, and somehow this idea was always thrown on the side. And recently, especially with the new, with the upcoming gravity wave experiments, it's again there's a new vogue of the structure at the horizon. People are trying to replace the black hole. People are trying to say, oh, you know, let's put something to replace the black hole. And there are many possibilities, and you know, essentially everybody and their brother is, you know, there are proposals. You know, gravastars, quark stars, boson stars, wormholes, quantum black boxes. You know, there's a whole slew of proposals that somehow at the horizon, there should be something. Because once you put something at the horizon, then the information can get out, then quantum mechanics is not violated, and then everything is perfect. But the problem is that all these configurations, all these attempts to put something at the horizon, again, they were ignored by the community for a long time because, again, nobody believed it's possible. And moreover, even now, all the proposals which are made, all of them have some hidden flaws. And it's one of my purposes to actually walk you a bit through the problems which you have with these things. I put this quantum pixie dust here because, it doesn't exist. Nobody has a proposal about quantum pixie dust, but, in terms of, solidity of physics, it's comparable to the others. So just to get an idea. So, if you didn't notice, this is supposed to be, this is an intruder, but it's at the same level of solidity as many of these other proposals. So what's the problem? We're trying to say, I have the black hole horizon, and I'm putting microstructure. I'm putting something there, and again, people have many names for these many proposals. And the question is, how can I build this structure? Well, there are problems. There are basically three very important problems which this structure must have. Problem number one is the growth of G Newton. So, black holes are very weird. Why are they weird? If I imagine increasing gravity, making gravity stronger, let's suppose I'm God and I have a knob and I make gravity stronger. I make it twice stronger. What's happening to the Earth? Gravity is twice stronger, the Earth gets compressed. What's happening to the solar system? Gravity is twice stronger, things get compressed. What's happening to the sun? Gravity is twice stronger, gets compressed. Everything in the universe, because gravity is an attractive force, if you make it twice stronger, everything gets compressed. Except one object, which is the black hole. The black hole horizon, if you make gravity stronger, the black hole horizon grows. If you make gravity twice bigger, the black hole horizon becomes twice bigger. If you make gravity 10 to 20 times bigger, the black hole becomes 20 times bigger. Everybody else becomes small, everybody else shrinks except the black hole horizon. So if you want to say, I'm replacing the black hole by quarks, grava stars, grava quarks, whatever you are using, your stuff, which is replacing the black hole, must also grow with gravity. And that's a very, very non-trivial thing to do. You cannot just say I'm putting a sphere of metal and I'm replacing the black hole by a sphere of metal, which you could imagine doing, because if you make gravity twice stronger, the sphere of metal is going to be crushed, it's going to become much smaller, and the black hole is going to become bigger. So you cannot replace the black hole with a normal object, built in a normal theory. Now, these microstate geometries which I told you about, they actually can have the black hole growth. And that's actually for us, actually at the beginning, when I saw this proposal by Matur that the black hole should be replaced by something, it was Gary Horowitz who basically told me, look, there's no way this can work. All these ideas are just, crap, because the black hole, grows, and whatever else you build is going to become smaller. But the thing which is nice is that in string theory, there are some objects which are called d-branes, which I told you about. Now these d-branes have a tension which goes like 1 over g string. The Newton constant is actually proportional to g string squared, and the d-branes of string theory are actually lighter. When g string becomes large, d-branes become light, because they are actually non-perturbative degrees of freedom. And these non-perturbative degrees of freedom, they become lighter as Gn. And again, in this solution which I told you about, there's some rotating black holes, some d-branes which rotate. And when you have rotation and you make an object lighter, it becomes big. So in these particular systems, it's actually the existence of non-perturbative degrees of freedom which form this horizons, this structure, the horizon. The structure, the horizon, must use non-perturbative degrees of freedom. You cannot do it if you just use gravitons, if you just use normal, nice, simple object. You must have non-perturbative degrees of freedom. And this is the first lesson. I put Yoda. I realized that I didn't put Baby Yoda. I should have really found Baby Yoda and put it there. But in the old slides I had Yoda, and then Baby Yoda appeared a few months ago, and I had no. I only realized that 1 hour before the talk, and I didn't feel like replacing. Plus, Baby Yoda hasn't spoken yet, so maybe we can still go with Yoda for a while. But the deep physics is that, again, in order to build this at the horizon, in order to replace the black hole, you must use non-perturbative physics. Now, in string theory, you have this thing. They are called d-branes. It took string theorists 20-something years to find d-branes. String theory was, people began working in the 60s and in the 70s. D-branes were discovered in 95. The role of d-branes was realized in 95. It took a lot of time to find these non-perturbative objects. And if you want to repeat this success in other quantum theory of gravity, whatever that is, if you want to replace the black hole, one of the ingredients is that one must find these non-perturbative objects. They are the ones. If you want to say I'm replacing the black hole in some other quantum theory of gravity, great, you can do it, but it has to be done using non-perturbative objects. It cannot be done using linear waves and gravitons. People have been trying this forever. It doesn't work, and the reason is, again, because everything gets crushed. All the perturbative degrees of freedom get crushed. Only non-perturbative degrees of freedom get actually expanded when gravity becomes stronger. In other language, there are people who do boson stars who are supposed to replace the black hole. There's another way to see this. Essentially, if you use a boson star to replace a black hole, I don't know how many of you know, but people who do gravity waves, for example, they use these boson stars to model their black hole replacements. Essentially, if you want to replace a boson star, to replace the black hole with a boson star, for a given black hole, you need one particular scalar field, which has to replace the black hole. So if you have a solar mass black hole you want to replace with a boson star, you need one field. A 30 solar mass black hole, you need another field. A 10 billion solar mass black hole, you need another field. And essentially you need an infinite number of fields, one for every value of your black hole mass to replace it. Somehow string theory has these degrees of freedom which have this role. Those of you, if you don't know what boson stars are, ignore the last two lines. Those of you who work on boson stars, this is again a way to see that this is not, they are not using these non-perturbative degrees of freedom. That's problem number one, and it's a big one. Problem number two is even worse. I told you that black holes have horizons, and this is, for example, a slice of a non-extremal black hole which has two horizons. There's an inner horizon and there's an outer horizon, and the horizons are null. Now, what are we trying to do? We are trying to say, we're replacing the black hole. We are putting at the black hole horizon some structure to get the entropy out, to solve the information paradox, to make the 10 to the power 98, to put all the 10 to the power 98 states there. We are putting something at the horizon, but the horizon is null. And usually stuff doesn't like sitting on null surfaces. Why? There's a GR dogma. You should not put anything at the horizon. And the reason is very simple. Because it's a null surface, if you put anything which is massive, you want to put a car at the horizon of the black hole, in order for the car to stay there, it has to go the speed of light. This thing goes with the speed of light. Normal stuff just falls in. Normal matter, obeying normal equations of motion, you put it at the horizon is null, it just goes in. Only very crazy matter can actually stay at the horizon and go like that. If you put a massless field, for example, again you can solve the massless wave equation in a black hole background. You solve the equation, you find that in a crossing time it's gone. Whatever profile you put in the black hole solution, the moment if that object obeys any normal equation of motion, any reasonable equation of motion, it immediately gets flushed in. You cannot put stuff there. This is really because it's a null surface. It's a very simple reason. And I'll explain in the future slides how in string theory this can be avoided. And again, the lesson is that if you don't have a support mechanism, if you don't have a mechanism to support your stuff at the horizon, if you don't have something to support you, gravity is just going to come in and flush you in. Most of the proposals which I had on the previous slide, they basically suffer from this principle, which I call the quantum coyote principle. If you know these cartoons with Willy Coyote, there's like this guy who runs after there's a bird which says like meep meep and goes and the guy runs very fast. Usually when the guy runs and ends up in this situation on top of the canyon, he basically goes there and he looks down and then gravity starts acting and gets you down and brings you down. But the quantum coyote principle says gravity doesn't work till you look down. And the problem with all these proposals to replace the black hole with something, if they don't have a support mechanism, they will do exactly like Willy Coyote. You ignore gravity, but once you look down, gravity comes in, and essentially you have this guy falling in, and you end up at the bottom of the thing. And this is the fate again of all these proposals and their brothers. Everybody who says I'm replacing the black hole with something, if you don't have a support mechanism, you just go flush into the black hole. Again, if you want to see this cartoon again, this is Willy Coyote, you know, falling down and crashing at the bottom of the canyon. I have this from Nick Warner, my collaborator. I have this is the slide which he's using, and I figured out, you know, for this class. Normally I don't use this in my talk, so, but you know, this is this is really I mean, I think for this class it's a good addition. Now, problem number 2, again, you need something to keep you there, and you know, again, you essentially have to go with the speed of light, and you know, it's very non-trivial.
Sorry.
Yes.
So going to point 2, so what is your insight or opinion about soft gravitons, for example?
Soft gravitons.
Soft charges.
So soft charges, first of all, they don't live at the horizon. Soft gravitons, there are gravitons which live at infinity, so that's the soft charges which are like energy living at infinity. And then if you put soft gravitons at the horizon, there are singularities. What I understand, if I understand. Now, soft gravitons are a way to cheat. The reason why you are cheating with them is that, you know, they really have no mass. So in a sense, you know, because they are soft, they have no mass. There's nothing to attract them. So they can actually stay there. The problem is, you know, they are singular. So as far as I understand, and okay, I'm not an expert in this, but I have colleagues who are. You cannot build at the horizon. You cannot use the soft gravitons to put them on the horizon. And moreover, if you do, you can put a few of them. But you can show very easily that the number of soft gravitons that you have available is much, much lower than what you need for the black hole.
Well, but there's but the fact that there's a boundary there.
It's not a boundary, it's a time like the problem is it's a null thing. So if you have a soft graviton which has again no mass, then you know you can put it there because you know there's nobody to attract it. But you know the moment you put anything which has a non-trivial energy momentum tensor, that thing is going to come in and you know fall in the black hole immediately.
Okay.
If you solve the wave equation for a normal particle, it's only soft particles which can stay there. But again, soft particles. Also, you can show that if you have them, they're not going to give you the black hole entropy. So they can be some extra things, but you know they're not going to be enough. So you can show this in ADS3. It's a very easy calculation, which was actually done by Jan de Boer a while ago using graviton gas. But I can do that. Problem number 3 is actually even worse. Problem number 3 is the following. Let's suppose you take a shell of dust. We all know from GR that if you take a huge shell of dust, mega big shell of dust, and you collapse the shell of dust, you form a horizon. Now, let's look at this Penrose diagram. This is our universe. This is the horizon. This is the shell of dust. Let's suppose I have my shell of dust which collapses, and at some point the shell of dust becomes smaller than the Schwarzschild radius, at which point the horizon forms. Again, when you have a shell of dust collapsing, it's becoming smaller and smaller and smaller. At some point, it's becoming smaller than the radius, than the Schwarzschild radius of the corresponding black hole, and at that point, the horizon forms. This is the horizon. Everything else which happens inside here, with the shell of dust, when the shell of dust keeps on collapsing, that's physics which is happening in a sense after the formation of the event horizon. Now, let's suppose you form this shell. And let's take a big black hole. So let's take a shell of dust which has the same mass as the biggest black hole of the universe. The biggest black hole of the universe is this TON 618 black hole, and the shell of dust is going to collapse. The curvature of the horizon, you can actually show that it's about 20 times g, which is actually quite a small curvature. So in a sense, physics is not expected to be very crazy there. So the shell is going to collapse, very happily, and it's going to keep on advancing, and it's going to keep on crashing for about 180 hours more, so about 7 days and a half. So for 7 days and a half, this shell keeps on collapsing. This black hole, TON 618b, has 1300 astronomical units of Schwarzschild radius. So we can actually compute how much time it takes for the light to go through, and it's again 180 hours of collapse time. So you form this, you have this shell of dust, you form a horizon, and then you keep on falling for 180 hours all the way here, and at some point, okay, this shell is going to become very strong, very quantum, very crumply. You'll have quantum effects, you'll have new physics, you'll have string theory or quantum gravity or dynamic triangulation, whatever you want. You'll have all the crazy quantum stuff you want. But that crazy quantum stuff will happen here, in this region which I denote here in red. However, the problem is that the horizon has already formed. The horizon has formed here 180 hours before this crazy quantum stuff forms. And moreover, the horizon, as you see in the Penrose diagram, is in the causal past of this crazy region. So whatever if you claim that I'm collapsing a black hole and I'm forming this crazy stuff and I have to replace the black hole by my stringy or by my favorite quantum gravity big fat shebang, the problem is this big fat shebang can only form here, can only form when everything is compressed, and when I reach the scales which are where my quantum gravity effects are supposed to become important. At this point when I'm here, my quantum gravity effects are small and tiny and teeny weeny. Essentially you can compute the tidal force, for example, on a human which falls down with the shell of dust. At this point it's 10 to the power minus 20 or something g. So gravity is very, very tiny. You can go through this place without any problem, and nothing should happen. There should be no quantum gravity effects here. The only place where quantum gravity effects can happen is here. But this is again 180 hours after the formation of the horizon. So how can I get my horizon to be replaced? Because what I want to do, again, all these proposals to solve the information paradox, to get everybody to be happy, to get quantum mechanics and GR to be friends again, all these proposals involve getting some big shell of stuff here. And the big shell of stuff there cannot be formed by starting from this stuff, because you have to go back in time 180 hours. And that's illegal. In all theories of physics, this should be illegal. So how can this happen? How can I actually form this stuff from this collapsing shell of dust? The answer is very interesting, and it's something which is called enhanced quantum tunneling. It's a phenomenon which is quite remarkable. What's happening is the following: the black hole, in this what I tried to explain to you before, is that it has a huge number of states. It has e to the s states, which again e to the 10 to the 98 states. Now all these states, we are trying to argue that they are given by horizonless configurations. When you have the shell of dust collapsing, at some point the shell of dust is going to be in a region. It will have the same size as a shell, as all these black hole replacement shells, and it can tunnel. It can undergo quantum tunneling. Now the tunneling probability is going to be very, very tiny. It's going to be, and you can estimate it, and we actually calculated it for some particular supersymmetric black holes, and this number is going to be e to the minus s. So e to the minus 10 to the 98 is the probability of tunneling from this shell of dust into one of these very non-trivial black hole horizon, one of these very non-trivial horizon-sized configurations. Well, however, you do have e to the s possible endpoints. So you have e to the 10 to the 98 endpoints. The chance of going into every one of them is e to the minus 10 to the power 98. So it's a very, very tiny chance to go into any one of them. But the overall probability of going into one of them somewhere is going to be over the 1. And that's again something which is a very weird phenomenon, and it only happens for black holes. By the way, this collapsing shell of dust, this was found by Oppenheimer and Schneider in 39. So nobody from 1939 until these papers realized that this can actually happen. Because again, everybody believed the collapsing shell of dust just forms a horizon. The only mechanism which can stop the horizon from forming, unless you want to go backwards in time for 180 hours, which nobody wants, hopefully. We don't want to go back in time for so much time. The only mechanism is to have this quantum tunneling. And again, this shell of dust will tunnel with probability 1. But again, it will tunnel because there's a very, very tiny probability of tunneling, but there's a huge number of available states, and the two things balance each other to give you a number of order 1. And essentially to do it, you must have e to the s horizon-sized microstates. So if you replace the black hole by some structure, by some shell, by something, again, if you use the structure at the horizon, the structure which you replace the black hole with must have a huge entropy, must have the same entropy as the black hole. Unless the structure has a huge amount of states in it, it will never form, because you just form a nice black hole. And again, so word of wisdom number 3, the structure must have the entropy of the black hole. This is again necessary. People do these gravastars. Gravastars are one way to replace the black holes. They were proposed by Mazur and Mottola, and they have no entropy. There's only one state. You can never form a gravastar because you'll be forming the black hole, and then there's no way to tunnel because the chance of going from a black hole to the gravastar is e to the minus s, but there's only one gravastar. So the chance of forming it is e to the minus 10 to the 90. So you'll never form it. Now this enhanced quantum tunneling is a very weird phenomenon, and again it happens because of two things. There's a tiny probability of tunneling, and there's a huge entropy of the final end state. Those are the two ingredients. Now you can ask me, why can this happen? No, I'm from Transylvania, I'm from Romania. I was born in Transylvania, so this is a fellow Transylvanian. And you can ask, why doesn't this happen? I have Count Dracula, and I do quantum tunneling, and I let Count Dracula tunnel into a big bar of chocolate. It can happen. Chemically, okay, the human body and the chocolate, they have comparable things. Maybe it's a low-fat chocolate, maybe it's a high-fat chocolate, depending on what kind of person you are. And maybe you have some extra minerals on the side. But more or less, you get the same. It's a comparable thing. And the question is, why don't I tunnel into chocolate? Because again, there's a tiny probability of tunneling, exactly like this black hole. But the number of n states when you have this thing is actually smaller than the black hole. It's not a small number, but it's a smaller number. And the only reason we don't do quantum tunneling into chocolate is not because it's a small probability. That's a small probability. There are many places where there's a small probability. It's because chocolate doesn't have a large enough entropy. If chocolate had the entropy of the black hole, we could be tunneling into chocolate or into many other things without a problem, because of this enhanced quantum tunneling. So again, the only reason why you don't tunnel into chocolate is because chocolate doesn't have. So if anybody asks you, well, why don't you do quantum tunneling into chocolate, it's because the probability is small. And normally when you say quantum mechanics, you say the chance of me tunneling to the moon is very small because the probability is small. But that's not enough. The probability needs to be small, and the number of available n states has to be small either. It cannot be too large. If the number of n states is huge, if the entropy of the resulting things is huge, then you'll be tunneling into that, even if the probability is very, very small. And homework, estimate the entropy of 100 kilos of chocolate. That's again homework for you guys. Shouldn't be very hard. It's just a chemical formula. I think you can find it on Wikipedia. And the probability of a human who has 100 kilos to tunnel into it. What's the probability of that? That shouldn't be hard either. I mean, it's just a bunch of molecules because, essentially the atoms stay the same, so it's just molecules moving around. So you can estimate what's the chance of jumping from one particular molecule to another one, and so on. Multiply by the 100 kilos of human we have, and then you can actually find what's the probability of tunneling into this chocolate. But the point is, we don't have this tunneling again because the entropy of chocolate is very, very small. If the entropy of chocolate were larger, we could be tunneling into it. So it's not good enough to just say I'm replacing the black hole, and here's one example of something to replace the black hole with, or here are 2 examples or 3 examples. Essentially, when you have some dynamics, you cannot get an end state which is just one very particular stuff. You must get solutions which cover all the possible phase space. You must get all the possible solutions of the system. And when you have, if you have 1 or 2 or 3 black hole replacements, but they're not good enough. You need to build e to the s of them. You need to build a huge number of black hole replacements, because this is actually what you need again if you want to form the structure at the horizon. And when you have a collapsing shell of dust, again you have the shell of dust collapsing. This is the horizon. You have the classical black hole, and then you have these very, very fine-tuned things like Grava stars, which again I can build 1 or 2 or 3, but a few of them. Or you have this huge amount of microstates which have an entropy which is again e to the s, which is e to the 10 to the 90 for our galaxy black hole. And the only way you can form structure at the horizon is if you have the entropy here, which is avoided entropy of the black hole. That's again the third problem. So those are the three big problems. First of all is the growth. The size has to be growing with G Newton. The second is the support mechanism. It's to have something keeping it at the horizon, which is not pixie dust, in the best of cases. And third, you need to have some tunneling. You need to have this enhanced quantum tunneling in order to form this structure. If you don't have all 3 of these ingredients, you are toast. You cannot build this structure at the horizon. And the purpose of the rest of my lecture is to explain you how to build structure at the horizon, how to get these very funny properties. We began an hour ago. Maybe we should go another 10 minutes or so, and then we take a break. Is that good? Okay. So until now, I didn't do too many equations. I only did a few things. I want to give you some idea how to build this structure at the horizon, how to build these configurations. In order to do it, we can take a very simple system of d branes in M theory, in string theory. So string theory has 10 dimensions. There's something called M theory, which is more complicated, which has 11 dimensions, but you don't need to think about those too much. The way to build a black hole is to always take 3 or 4 types of d branes and put them on top of each other. And in this particular case, there's a black hole which was built by Strominger and Waffa a long time ago, which is obtained by taking a torus. You take a 6 torus. Imagine taking 6 directions, and then you put an M2 brane along the direction 1, 2, another M2 brane in the direction 3, 4, and another M2 brane in the direction 5, 6. This is a solution which has a big black hole area, and the entropy is given by, again, this number 2 pi times n1 times n2 times n3 in this particular case, which I call here n1 n5 np, but you can think about them as n1 times n2 times n3. This solution has an entropy, and I told you before how to count this entropy using d branes and using a microscopic system. Now the solution looks a bit more complicated than what I showed you before. There is factors of z1, z2, z3 to the power minus 2/3, multiplying the time. There's a rotation vector which I didn't discuss too much, and moreover there are some electric fields. This black hole is not a neutral black hole. This black hole has some charges because these M2 branes have a charge. These branes are charged objects. Now the charge is embedded by some 4 form in M theory, which has some legs in the direction 1, 2, 0i, 3, 4, 0i. So this black hole has actually 3 types of electric charge, which are given by this particular. So again, it's all color coded. The blue d brane has the blue electric field, which has a very simple value given by this number. And this black hole, just a second, let me get. So this black hole is also supersymmetric, and you can see it's supersymmetric if you do a bit of exercise. I mean, it's something which is not very hard. Essentially, somebody who is a grad student in the first year in string theory should be able to do this calculation in half an hour. The fact that the function z appearing in this place in the electric field is the same as the function z appearing in the metric. This should give you a hint that this black hole has the same charge and mass. It's a hint. I'm not going to go into more details, but there's a relation when you have this black hole. There's a relation between charge and mass, and this black hole is an extremal black hole. It's a black hole which has the same charge and mass. So it's a black hole which is supersymmetric and extremal. Yes.
Why do you need to have more than one?
If you have a single d brane, you don't have this fractionation thing. So I told you that to get the entropy of the black hole, you need to get a huge amount of states. Mm-hmm. When you have a single d brane, just by itself, you can ask how much entropy do I have from a single d brane, and the answer is a single d brane has 256 states, grand total. Not too much. When you have 2 d branes, you put them next to each other, you can ask how much entropy do I get from 2 d branes, and then the answer is you get e to the power square root of q1 times q2. Mm-hmm. That's a big number, but it's not enough for a black hole. If you want to get a black hole, you need the number which is over the square root of q1 times q2 times q3. And it so happens that the only way to do this is to either have a black hole in 5 dimensions. This black hole is actually in 5 dimensions because where in M theory there's 11 total dimensions. This is time, this is a 6 torus, so there are 5 space-time directions. So you can have a black hole in 5 dimensions using 3 charges, which has 3 charges, or you can have a black hole in 4 dimensions which has 4 charges. Now 4 charges is actually a string theory language, because if the charges are equal and you compactify to 4 dimensions, it looks like a nice raster nostrum black hole. So when I say 4 charges, it has some charge which has string theory origin coming from 4 types of d branes. But those are the only 2 supersymmetric black holes which one can build. And for now we're going to do the supersymmetric black holes because they're easier. They're the ones where we can do some progress. Then once we do the supersymmetric ones, we'll be doing the non-supersymmetric ones, which are much more complicated. But for now we'll be doing the supersymmetric ones. So all the ones we have 3 charges and have the mass equal to the sum of the charges.
So then you cannot have a Schwarzschild.
No, at this point no. I'll do a Schwarzschild later. I'll go to a Schwarzschild later. But the way you build stuff in string theory and the way things are done, you build first the supersymmetric. The supersymmetry is like a big scale. Is like a big what the French word is scaffolding. That's the English word. Échafaudage. I had the French word in mind. If you live too much in France, you get. So it's a scaffolding. Use the scaffolding, and then you climb up. You build it up using supersymmetry, because that's very helpful. Once you have supersymmetry, understand a bit how things are going, then you actually go ahead and you break supersymmetry, and you look at things which are far away from supersymmetry. So first of all, you look at near supersymmetric black holes, and then you go away from supersymmetry and you get to Schwarzschild. And I'll get to that, this is the whole, but at this point again, I'm building the scaffolding. I haven't reached the second level. I'm just doing the scaffolding. I'm doing just one black hole. By the way, the things which I showed you before, all these three criteria, they are the same, whether you have a supersymmetric black hole or non supersymmetric black hole. These three criteria are always there. The three problems which I told you, the entropy problem, the collapsing problem, and the size problem. They are there regardless of whether you have supersymmetry or not. So once you can solve them in one setup, then we say, okay, we solve them there, we have something to hatch on, and then we move away from supersymmetry in order to get to the real world. So again, this black hole is supersymmetric, has these charges and has these very fine electric fields. Now what we want to do? We want to take this black hole and to say, I want to replace this black hole. This black hole has a horizon. I want to replace the black hole by something which doesn't have a horizon. Where is the horizon coming from? I told you before there's these functions z1, z2, and z3. They look like something over r squared. And the horizon is at r equals to 0. So from the perspective of this space, the functions z1, z2, and z3, they appear to be harmonic functions sourced by a delta function source at some location. They are really singular points, and the singularity, the place where they blow up, the place where, so again, in the black hole solution, they look like 1 over r squared. The place where they blow up is the place where the horizon of the black hole is. If I want to have no black hole, I want to be able to take these guys and I want to separate them. I want to get some non-trivial size to this system. And to do that, what I can do as a self-respecting string theory is I can add some extra d-branes. String theory has again many d-branes, and in this particular case, it's something which, again, I spent some time trying to understand, but you can convince yourself after. It's not very painful to convince yourself that you have to add 3 more types of d-branes, which are called amphibranes, which are color coded here in this yellow, brown, and red colors, which have again these particular orientations, and the only effect of these amphibranes to the system is to add these yellow, brown, and red forms, which are actually 2 forms in the transverse space transverse to the d-brane. So again, you have a black hole, which is a point in R4 and time, and now I put a curve in R4, I blow my point into a curve, I get my space-time to be, and when I do that, I don't have a horizon anymore. The horizon only comes because all my charges, everything is at a point. That's how I get the horizon. Once I blow up things, I don't get a horizon anymore. I don't get a normal black hole horizon. And actually, you can show that if you blow up this thing up, you actually get a black ring, which is a different object. But I'm not going to get into that at this point. But the point is, the solution of this system depends on these 3 magnetic fields, again, which I can call G1, G2, and G3. This function z, and this vector k, which is the rotation vector of this problem. And then what we realized, and what we realized with quite a bit of happiness, was that if you want to get supersymmetric solutions of this system, the supersymmetric solution of this system, because again I have a supersymmetric black hole, I want to get supersymmetric solutions to replace it. The supersymmetric solutions have actually been solved using a system of 4 layers. First of all, you have some base, which is again some 4-dimensional space, which is R4 in this particular case, but I can take it to be some generic 4-dimensional hyperkähler base. Hyperkähler is a math property. If you don't know what it is, I'm not going to get into it. Then you have to choose some self-dual fluxes. These G's have to be self-dual, so I have 4 dimensions, and my G has to be equal to its self-dual. And then my functions Z are sourced by the product of these G's, and then my rotation vector is sourced by this combination of G's, which are electric guys, and Z, which are magnetic guys. That's the way the equations work. Those are the equations which are governing all the possible supersymmetric solutions which have a 4-dimensional hyperkähler base. Now, there's a simple example of a hyperkähler space which I want to get into. I'm not going to have many more equations, just this and one more slide. So if you don't follow don't despair. I'm not jumping into math. I'm just giving you a bit of an intuition of how these solutions are built. But then I have the physics. I mean, those of you who know a bit of geometry, this is useful. So there's a space which is called Gibbons-Hawking or top knot. Now, this space, which looks very simple, it's a psi circle fibered over 3 dimensions. This space is actually, if this function v is equal to 1 over r, you can actually show that this function a has to be equal to 1 plus cos theta, and then the whole solution here is equal to r4. Even if this doesn't look like r4 is dx1, dx2, dx3, dx4. But this solution, which has x1, x2, x3, and the circle fibered over, when the function v is equal to 1 over r, is exactly the same metric as R4. This guy has the same metric as R4. It's a nice exercise. If you have never done it, and you're a person who does GR and black holes or quantum gravity of another sort, it's a very good exercise to do. Just take this metric, the Gibbon-Salking metric, with one center, v is equal to 1 over r. The a, you can find that it's equal to cos theta, and plug it in here and change variables to get R4, to see how R4 comes from this space. And in general, all the solutions to the system were shown by Gaudet and Gutowski and by us that can be determined by 8 harmonic functions. So you basically have to find the solutions of the system. You take this 3-dimensional base space, and in this base space you write harmonic functions, and these harmonic functions give you all the possible supersymmetric solutions of the system. Now, to give you an example, one type of such a solution, so let's say this is the base space, which again looks like v to the minus 1 times this, v times this. One type of a solution asymptotically to R4. So I have a black hole. The black hole has R4 at infinity. Therefore, if I replace the black hole by something, the infinity should be preserved. So at infinity, my function v should go down like 1 over r. Because again, 1 over r is R4. And in this particular case, you can see that the function v has a 1 over r, but then it has actually 2 more poles. Has a pole which is at r equals to a with a minus sign, and has a pole which is at r equals to b. So instead of having R4, which is a nice clean space, now I got a space which is more complicated. Why is it more complicated? Well, if you look at this metric, there's a v to the minus 1 multiplying this guy. This guy is a circle. Now, what's happening at the point r equals to 0? V goes to infinity. V goes to infinity, it means that V inverse goes to 0. So what's the size of the psi circle? 0. What's happening when you go to r equals to a? V goes to minus infinity, but for now just think about infinity. V inverse goes again to 0. And therefore, at the point r equals to a, the psi circle is again 0. In between, the psi circle is big. So I have a circle which is 0 here, 0 here, and in between grows, and then becomes smaller, and this forms what? Circle, big here, small here. What is this? It's a ball. It's a two-sphere. So a ball or a two-sphere is formed when I have, if I think about slicing a ball, at the north pole I have a circle which is 0 size. As I go down, my parallels are bigger and bigger and bigger. At the equator they are the biggest, and then further down they are again small. So if I slice a ball using parallels, that's exactly what I get. I get a circle which is shrinking at one point at the north pole, shrinking at the south pole, and is big in between. But now I'm cheating because I have another circle. So I have another ball between the point r equals to 0 and r equals to b. Between r equals to 0 and r equals to b, the same thing happens. At r equals to 0, this psi circle is 0 size. R equals to b, the psi circle is 0 size. And in between, it's big. So I have another topologically non-trivial ball between the point r equals to 0 and r equals to b. I'm not going to get into this interface story. So then, in general, one can build solutions where one has many poles of the function v, and between every two of them there's a topologically non-trivial cycle. There's a topologically non-trivial ball. So the way the space-time looks like, I had before a black hole which was a singular point, and now I have a bunch of bubbles. I really have bubbles, and those are bubbles. There's a bubble here which is topologically non-trivial, another bubble here, another bubble here, another bubble here, another bubble between those two, another bubble here. I get a space-time which is full of bubbles, which has a huge number of bubbles. Now, these bubbles have actually flux on them, because again I told you that you have this two-form flux, and you can show that these bubbles, that if you look at the flux on these bubbles, the flux is going to be non-zero. So then the way to replace the black hole and to create the structure at the horizon is going to be to blow up bubbles in my space-time, exactly like when you think about having a balloon scheme, a balloon, and then the skin of a balloon, and then you do this thing with your mouth and you blow up a bubble, and then you blow up and you blow another bubble. That's exactly what we are doing. We are blowing up topologically non-trivial bubbles, and these bubbles are actually replacing the black hole. So then I find a solution at the end of the day which has this particular structure. Again, I have many bubbles, The sum of the charge of the bubbles is 1, but I don't want to bother you with that. And the point is, I have replaced the black hole. Now you can ask, how did I replace the black hole? The black hole had the charge, had the mass, has an angular momentum. Where have they gone? Now the answer to the first question is, the black hole had the charge. What's the charge? The charge of an electron is the coupling to the electric potential, to A0. You have the vector potential, and A0 is the zeroth component of the vector potential. The charge is the coupling in the Lagrangian to A0. Now, in the particular supergravity theories which I use to build up these black holes, in string theory and in 11-dimensional supergravity, there's a term in the Lagrangian of the form A wedge F wedge F, or epsilon 1, 2, 3, 4, 5 times A1 F to 3 F 4, 5. There's a term which has an epsilon contracted with three forms, and in this particular example, you have these bubbles. The bubbles have a magnetic field. They have an F which has no component along 0, which is a magnetic field. And you have two magnetic fields acting as a source for the electric field. So before I had the black hole, I had the horizon. And now what I have bubbles. And on the bubbles I have magnetic fields. That's all I have. And the charge of my black hole is obtained now from these magnetic fields wrapping these bubbles. Moreover, the mass of the black hole doesn't come from a horizon anymore, doesn't come from a singularity anymore. I don't have any more like a singularity. The only thing I have bubbles and fluxes, but the bubbles have magnetic field which have an energy. So the energy of my magnetic field is the mass of the black hole. And the angular momentum of my black hole comes from a pointing vector. You know from electromagnetism that you have an E and a B which are crossed. There's a non-trivial angular momentum, and that's given by a pointing vector, and that's exactly where the black hole angular momentum is coming from. So this procedure actually of blowing up bubbles replaces the black hole with something which has a non-trivial size and has non-trivial bubbles. And essentially, the classical black hole, you know, the nice black hole which you have in your solutions, has two scales: the Planck scale, which is again the scale when quantum effects become large, and the mass of the horizon. Now, what we have done, we have replaced the black hole. So we have formed some structure above the horizon at some maximal redshift. The horizon is down at an infinite distance. So there's a size of this. So my structure which I'm building is at some distance above the horizon, and that's giving me this gives me some redshift if I think about it in these terms. The redshift to the horizon is infinite. Sorry, and then I also have the size of the bubbles. I have some bubbles. I can have big bubbles. I can have small bubbles. You know, it's up to me. I can do all of them. So this is the mechanism which replaces the black hole with replaces the black hole. Let's take a break now for 15 minutes, and then I'll come back and I'll tell you why those things don't collapse and how to live with them. So the big question is, okay, you have this configuration which has bubbles on cycles, and the question is, why doesn't this configuration collapse? You have these bubbles, and normally if you put a bubble of soap, for example, you know, you pop it and it's just going to collapse. And normally, you know, if you want to put a hole in space-time, for example, you know, in our room, if you want to put a hole in space-time, that hole is going to close immediately. You don't have, you know, space-time hates having bubbles. Now, the reason, I'll give it on the next slide. What I want to emphasize is the following. If you look at these solutions, which have again Gibbs-Hawking centers, which have some charges which are plus and some charges which are minus. From the perspective of string theory, if you compactify these solutions down to 10 dimensions, these solutions actually have centers. I mean, these points become some actual d-branes. But the d-branes which you get are not normal d-branes. They are d-branes which have normal positive mass and positive charge. They are the ones which are there at the positive centers. But then you get some other d-branes which are very weird, which have negative charge and negative mass. But somehow the solution still makes sense. And that's a phenomenon which happens in string theory quite often. You also have orientifolds which have negative mass and negative charge. It is those objects which, from our perspective, if you ask why do these bubbles resist at the horizon scale? Why don't these bubbles get flushed in to the black hole along with everybody else? What's the reason why these bubbles resist and have a support mechanism, unlike, you know, other stuff which one wants to put at the horizon? The reason why the bubbles resist is because, from a lower dimensional perspective, they are made from these objects which have negative mass and negative charge. And this negative mass and negative charge assure that even if you go with the speed of light, you're actually not going to be, you're not going to have a problem. And from a 4D perspective, it's a highly unusual matter. So if you want to mimic a black hole, to say, let's try to replace the black hole by some object, and let's try to understand the physics of this object, and what this may give us for gravity waves and so on. It's a very weird object which you have to use, because again, the ingredients of these bubbles from a 4D perspective in your 4D effective theory look like negative mass, negative charge centers. So it's a very weird ingredient from a 4D perspective. Now, why don't these bubbles collapse? It's very easy. You take a sphere which has a flux on it, and you can ask, why doesn't the sphere collapse when you have a sphere which has flux on it? Well, the flux is quantized, first of all. When you have, again, whenever you have a sphere which has flux, the magnetic flux is quantized. That's a requirement of regularity of the solution. So the integral of F2 on this sphere is equal to 4 pi times n. It's doubly quantized here, but it doesn't matter. So if you write F2 in using coordinates on the sphere, I have a 2 sphere, my coordinates are theta and phi, just the usual 2 sphere from my nice good old math class. So F2 can be written as n times sine theta times d theta times d phi, or otherwise in the language with indices, f theta phi is equal to n times sine of theta. Now my 2 sphere has a metric as well. The metric, again, there's a radius r, so g theta theta is equal to r squared. Usual stuff. I mean, this is just basic stuff. G phi phi is equal to r squared times sine square of theta. So then if I look at the energy of my system, if I ask how much energy does the flux on the sphere have, the answer is g theta theta with the legs up, g phi phi with the legs up, f theta phi. And if you compute that, you find that this number goes like n squared over r to the 4. So if my sphere has quantized flux, and then to squeeze my sphere to make it smaller, my sphere says, hey, my energy blows up. Because again, the energy goes like 1 over r to the 4. So my sphere with flux actually wants to expand. Gravity, on the other hand, wants to pull it in. And then there are some equations which give you the balance, and you can actually find it in this particular system. There are some equations which are deciding the balance of this game, which determine the size of the bubbles. But the bubbles will never, ever shrink because they have flux on them. And when you have a bubble with flux shrinking, the energy of the flux becomes infinity. And then the flux says, hey, my energy is becoming infinity, so things are not nice. So this is the reason why the stuff stays at the horizon and doesn't collapse. It's because it has bubbles with flux. Now, you can also build more general solutions. So I told you that you have the solutions which have bubbles and Gibbons-Hawking spaces. These solutions have an isometry, which is a U1 isometry, which is a spherical isometry. They are easy to build. But when you have isometries, you lose physics. Again, if you want to look at the system with the largest isometry, with the largest symmetry, the dynamics is very, very little. The system which has no symmetry dynamics, there's plenty of dynamics. And the whole smart thing about being a physicist is to choose enough symmetry to be able to do calculations, and not too much to be able to kill the dynamics. So somehow you want to find the systems where there's still some symmetry so that you can calculate, but there's still freedom and interesting physics to understand what's going on. If you put too much symmetry, you freeze the dynamics. Ice is perfect. Ice is nice symmetry, but there's nothing happening. Air is much more chaotic, but it doesn't have any symmetry, so it's much harder to calculate. So you can actually find configurations where the symmetry is broken, which is an arbitrary shape, and you can count the entropy on them, and you get some number which is not the black hole number, but still a large number. So we can, instead of getting e to the 10 to the 98, you get e to the 10 to the 70 something. Large enough numbers. We're getting a huge number of solutions, but we're not yet reaching the black hole point. You can also build a more general solution. You can actually take a D1D5 system, which I told you before. This is the one which gives you the black hole, and if you put a momentum wave on this D1D5 system, you get a shake. You get a shape mode. It's like when you have a guitar string, you pinch it, you get some traveling wave on this D1D5 system. So there's a momentum wave which makes it wiggle. And then you can also take this D1D5 system and you can do something which is called blowing it up into a super tube. And then you can find a solution which actually has an arbitrary function worth of variables. So you see, this D1D5 system, you asked me before, why can't I get an entropy from a single D brane? A single D brane has, again, a very small number of states. When you look at 2D branes can actually form this object called the supertube. And the supertube has an arbitrary shape. And because the super tube has an arbitrary shape, it has a large entropy. Classically, the entropy is infinity because, an arbitrary function is an infinite number of Fourier modes, and an infinite number of Fourier modes that are infinite degrees of freedom. But if you quantize, you find that these curves of arbitrary shape have a finite entropy. And this is the way the microstates of the two-charge system look like. This is not a black hole, this two-charge system. To get a black hole, you need to put momentum. And what we are arguing is that to get the microstates of the black hole, we have to put these super tubes, which are again two-charge configurations, D1D5 configurations of arbitrary shape, and you want to put momentum on them. And when you put momentum on them, you basically get shapes. But the shapes are not shapes of a single variable. They're actually shapes of two variables. You see, you have an arbitrary shape in this direction, and you have an arbitrary shape in this direction. And these objects, we call them superstrata. We conjectured them with Jan de Boer and Masaki Shigemori, who was a postdoc in Amsterdam back many years ago. Wow, 8 years, I'm getting old. And we call those guys superstrata. Now, superstrata, the name came from this nice strata towers which were supposed to be built in Dubai, which this is some hotel which has a cross section, and if you look at the cross section, it changes shape and changes orientation as you go. This is what the architect planned. What came out was this, and we kind of felt the same. We had this idea, so superstrata, we'll build all of them. We're going to find the more general solution, function of two variables, will be rich and famous, and so on. Once we sat down and did it, it became it, and it ended up being quite painful. It took us quite a few years to find these things. And again, the principle is very simple. You have a super tube, which is a D1D5 super tube, and the super tube is at some location, and it can wiggle in this psi direction. There's another direction, which is the D1D5 common direction, which is the V direction, and you can actually build solutions which depend on V only, or you can build solutions which depend on psi only. And in principle, you can construct solutions which depend on functions of two variables, f of psi and v. And we are able to do them about 4 or 5 years after constructing the original superstrata. Again, they look horrible. And more recently, my student Pierre Hyman and Daniel Marison, who is a student in Amsterdam, and Robert Walker, who is a student in Saclay, they were able to find even more solutions which are parameterized by functions of 3 variables. So you give me any function of 3 variables, arbitrary function of 3 variables, which corresponds to a triple infinite set of parameters, and you can build a solution. This is the largest family of solutions known to mankind. And again, they look horrible, but we are able to do them. And essentially these solutions, we were just able to construct these huge families of solutions. They are cohomogeneity 5. Those of you who know black hole solutions, the Schwarzschild is cohomogeneity 1, Kerr is cohomogeneity 2. Those are cohomogeneity 5. So they're horrible, but we're able to build them. And we call this paper Habemus Superstratum because we are so enthusiastic. The way people, when they elect the Pope, they say Habemus Papam. They say we said Habemus Superstratum. We're so happy that this thing came out. It's again the biggest family of solutions known to mankind, and there's a huge number of such solutions. And we're also able to find something called deep superstrata, which have a long throat, which again the black hole has an infinite throat, and the solutions have a huge throat, which looks exactly like a black hole, but they have a cap at the bottom. I'm not going to get into this. Quantum gravity in ADS2 because it's a tangential thing. So the supersymmetric story for the microstates at this point is that we have a huge number of them. We're able to build this huge amount of solutions. The entropy we have at this point is still not the black hole entropy. The black hole entropy is Q1 Q5 Qp to the 1/2. The entropy of the smooth solution is Q1 Q5 to the 1/2 times Qp to the power 1/4. So we still don't have the more general solution. We are still trying to find it. We think we understand what the ingredients are, but it's still something which we are progressing. But again, if you think about numbers, this is 10 to the 98. This is 10 to the 90 or something. But we have e to the 10 to the 90 solutions. The number of solutions we are building is enormous. This is again the biggest family of solutions known to Einstein equations. Moreover, this from an ADS-CFT perspective, the solutions we are building are dual to the states which live in the typical sector, so in a sense they capture the right black hole. They capture the right black hole physics. For example, you can show that in a black hole, for example, the black hole has a temperature, and when you put stuff in a thermal bath, it decays. In these microstate geometries, there's still, even if there are smooth solutions, there's no horizon, there's no temperature, naively. But if you put stuff in them, it still decays. You get exactly the same thermal decay as a black hole, even if you have no horizon, you have no temperature. You get exactly the same thermal decay, but if you wait long enough, you can recover the information. So in a sense, you have the same, you get the same thermodynamic features as the black hole, but if you wait long enough, the information comes out. So in a sense, this is happy with quantum mechanics. This is, these solutions, you can see that, they are happy from the perspective of quantum mechanics. So what's the story? I told you before that Strominger and Waffa, they count entropy, they count the microstates at zero coupling. They essentially count things in the regime of parameters and gravity is not present. And they find all these strings and branes which have the black hole entropy. What we are claiming is that as you increase G string, as you make gravity stronger and stronger and stronger, these configurations become, all the Strominger-Waffa microstates become this kind of horizonless configurations, and essentially the states of the black hole, the typical states of the black hole, the ones which give you the entropy, they actually grow, and essentially they become these geometries. You never get a geometry which has a horizon. That's what we're basically claiming for the extremal supersymmetric black hole using this calculation. Now the problem, and there's a similar story which I'm not going to get into for non-supersymmetric extremal black holes. Extremal black holes have zero temperature, but you can have supersymmetric ones and non-supersymmetric ones. There are some differences which are complicated and subtle, but I'm not going to get into them. The main problem is, as you asked before, what about Schwarzschild? Because in the real world we don't have extremal black holes. Maybe there are some Kerr black holes which are maximally spinning, which are close to extremality, 98% of extremality, but we don't have extremal black holes in the real world. We have non-extremal black holes. What to do with non-extremal black holes? So first of all, the question, why are we destroying the horizon? Again, we discussed before that we want to replace the horizon, and I told you that you have to replace the horizon because otherwise quantum mechanics is unhappy. But why is this happening? Why is the horizon being destroyed? And the answer is that the space-time has a singularity. The space-time, the solution which has a horizon, the Schwarzschild solution, even if the singularity is behind the horizon, the solution is still singular. And when you have a singularity in string theory, it's something which we have learned over years and years and years of research. When you have a singularity, at the singularity you can have some low mass degrees of freedom. Now, these low mass degrees of freedom can live there. And then by the uncertainty principle, when the mass of your system is very, very small, then when your P is very, very small, your delta P is very, very small, your delta X is going to become huge. So when you have a singularity in a space-time, and this is again a lesson, all of you who do general relativity, if you ever have to deal with any supergravity solution or any solution of Einstein's theory, if you have a solution and you say, my solution is singular here, and the curvature is large here, but I go 10 kilometers away, and I can do physics here, even if I have a singularity there. That's wrong physics. Because the singularity can have modes which have low mass. If you don't understand the physics of the singularity can have modes which are low mass modes. Low mass modes, by the uncertainty principle, they're going to have a huge delta X. And therefore, they're going to mess up your space-time and destroy your space-time at a scale much, much bigger than the scale where the singularity is important. They're going to destroy your space-time on a macroscopic scale. And we see this happening in string theory all the time. There's something called Polchinski-Strasser, Klebaron-Strasser, giant gravitons, LLM. There are many examples of string theory configurations where some singularity which has 1 centimeter, if you look at the physical resolution of the singularity, becomes 1 kiloparsec. And this is again happening because singularities can have these low mass degrees of freedom, which can actually destroy the space-time. Moreover, there are some circumstances when these quantum effects can be large, even if you don't have a horizon, even if you don't have a singularity. There are some examples when quantum effects can become large, and that's something which Jan de Boer and his students Edith van der Blecken showed, and we also showed with Nick Warner. Essentially, there are some limits when quantum effects can become large, even without having a singularity. And the reason why this particular black hole singularity has this power to destroy the space-time has to do with this phenomenon which I told you before, which is called fractionation. You put n1 d1 branes, the mass gap is 1 over n1. You put n1 d1 branes and n5 d5 branes, the mass gap is 1 over n1 over 5. You put n1 d1 branes and 5 d5 branes and k monopoles, some other species of beasts, the mass gap becomes 1 over n1 times n5 times nk. If the mass gap is 1 over n1 times n5 times nk, the size is the inverse of the mass, which is n1 n5 nk, which is the horizon size. So you can see that if you have d-branes, these d-branes actually they have these low mass degrees of freedom. They destroy the space-time on a large scale, and this can happen not only for supersymmetric black holes but also for non-supersymmetric black holes. If you look at all the non-supersymmetric black holes which one builds in string theory, you can write their entropy in this particular form, which is very intriguing. I told you before that the supersymmetric entropy is equal to 2 pi times n1 to the 1/2 and 2 to the 1/2 and 3 to the 1/2. When you have a non-extremal black hole, a non-supersymmetric black hole, you can actually think about this black hole as coming from branes and anti-d branes together. And if you write the black hole made from branes and anti-d branes, you can show that the entropy of this black hole really comes from d1 branes and anti-d1 branes, d5 branes and anti-d5 branes, momentum and anti-momentum. It really has it really has essentially these non-extremal black holes really have this physics that essentially most of their entropy comes from these brain anti-brain pairs. It's a very this formula looks like numerology. There's nothing. This is not. I mean, this is just numerology based on how the black hole entropy looks. Nobody understands microscopically where this formula comes from. But the suggestion is that because of this thing, the entropy of this black hole is given by branes and anti-d branes, and this system always has a mass gap which is of order 1 over n1 times n2 times n3. Again, because these d branes are fractionating each other. And they're creating these very small mass gaps. And these very small mass gaps, they are the ones responsible for destroying the space-time on a large scale. That's why because of these mass gaps, which that actually the singularity is so powerful and can destroy, a huge amount of space-time, a huge amount of space-time. Now, this is all for the extremal black hole, except the last slide. And the extremal black hole, again, what are we showing? We are claiming that you have the extremal black hole. This is the Penrose diagram of the extremal black hole. This is the infinity. This is the horizon. This is the singularity. And we are claiming that essentially the singularity gets resolved by these quantum effects, by these effects which mess up the space-time. And it gets resolved all the way to the horizon, which is, again, this particular curve. Now, this makes sense because, again, this curve and all this space-time is in the future of the singularity. So in a sense, the singularity gets resolved by these modes, which mess up the physics. But I told you before that, so this, for the extremal black holes is reasonable. But for non-extremal black holes, and what the fuzzball and the firewall arguments imply is that for non-extremal black holes have two horizons. There's an inner horizon, which is here. There's an outer horizon. And for non-extremal black holes, there are two possibilities. One of them is that the singularity is going to be resolved all the way to the inner horizon, and then you have empty space-time inside, and then you have the outer horizon. Or that the singularity will be resolved all the way to the outer horizon. Now, in order to solve the information paradox and to be happy with quantum mechanics, this must happen, and not this. But our extremal calculation, which is again the previous, for the extremal black hole, which is here, this is the extremal solution. You don't know from the extremal calculation whether the singularity is going to be expanded all the way to the outer horizon, because for the extremal black hole, the two horizons coincide. So the only thing you know is that for the extremal black hole, the singularity is resolved at the scale of the horizon. But once you go non-extremal, the two horizons separate. And then you have no idea whether our calculations and all this work implies that for the non-extremal black holes, this will happen, the red arrow, or the blue arrow. What's going to be happening? And to do that, you have to calculate. So in order to do that, in order to understand whether the singularity of the black hole gets resolved to this scale, you have to construct microstate geometries. You have to construct microstate geometries for non-extremal black holes. And one has to build lots and lots of such solutions. Problem is that non-extremal black holes are not supersymmetric, and therefore to solve them, you need to build, this is a slide which remained. In order to solve them, you need to solve second order PDEs. Second order partial differential equations, which depend on two variables at least, of 10 functions, 15 functions. Good luck. This has not been done. Maybe with numerics it will be done in the future. This is beyond the state of the art mathematically. Nobody can do it. So building these things, the reason why we could do it for supersymmetric black holes is because supersymmetry makes these equations much easier. Supersymmetry makes the second order equations factorized into first order ones. And then they're easy to solve. If you don't have supersymmetry, you have to solve the equations from scratch. And solving them from scratch is a complete pain. And again, nobody has ever found even one such solutions. To give an example, Einstein found the equations and Schwarzschild found the first solution in when did Schwarzschild find? In 1918? Or 1917? I forgot, the Schwarzschild solution. 16, okay. And then Kerr, the solution, so the Schwarzschild solution depends on one variable. The Kerr black hole depends on two variables. That's cohomogeneity 2. But it's still a very simple solution. When did Kerr find it? 60 something, 63, 67. But it took about 50 years. It took about 50 years to find the solution from one variable to two variables. Now, hopefully for us it will be taking less, but again, we are hiring numerical postdocs where we have tools and we think we have. But to build a huge amount of solutions, well, again, we're trying to build again e to the power 10 to the 90 solutions. We're trying to build a huge number of solutions. To build them for non-extremal is very complicated. Now, if you cannot build them directly, there's a Romanian saying, I'm from Romania, you probably realize, do not pray to the saint who doesn't help you. If you cannot build the solutions exactly, there's a way to build them, there's a way to look at them. And what one can do, one can construct solutions near BPS, near supersymmetric solutions. Instead of looking at a full non-supersymmetric solution, one can take a supersymmetric one, and you can add an object, you can add some type of energy, which is going to mess up, which is going to increase the energy of these solutions and make this thing non-supersymmetric. And this process is exactly the same as what people do when they do string cosmology. When they do string cosmology, they take some compactification and they put an anti-D brane, which lifts up the cosmological constant. Here, if you put an anti-supertube or an anti-D brane, you actually can lift up the mass. And you can get the mass to be bigger than the charge, and you can get the solution to be non-extremal. And then you can build these solutions. This is the way the potential looks. So if you look at one of these bubbling geometries, it has some ugly topology, has some ugly cycles. But if you look at the potential for a probe D brane, which is again this guy in red, the probe D brane, you see, in here there's a metastable minimum, in here there's a metastable minimum. But then from here it can decay. So you can go over this here and you can go down. This is a supersymmetric minimum. If you go here again, there's a metastable minimum, there's another metastable minimum, there's also another one here, and then you can decay again to a supersymmetric one. So this particular system, if you put a probe D brane, a probe anti-brane, it actually has a bunch of metastable minima, and all these metastable minima correspond to microstates of the near extremal black hole. Not non-extremal, but near extremal. So at least very close to extremality, it looks like, this is the picture, it looks like the singularity gets resolved all the way to the outer horizon, which is again what we want to happen. What about other black holes? What about far away from extremality? The problem is if I give you this Penrose diagram and I ask you which black hole does it describe? Does it describe the near extremal black hole, or does it describe the Schwarzschild black hole which has one electron? A Schwarzschild black hole, which is the nice big fat Schwarzschild black hole, which has the mass of the sun, and you put one electron on it. It is the same Penrose diagram. The only thing which differences are the scales. But this Penrose diagram describes both near extremal black holes and the Schwarzschild plus one electron. And therefore, if for one of these black holes, for the near extremal one, string theory says the singularity is resolved all the way to the outer horizon, the same should be happening for Schwarzschild plus one electron. The singularity should be resolved all the way to the outer horizon. But we don't know how. We don't have the solutions. We have not understood. We're not able to build up these things. The only thing which we can build up explicitly are the near extremal ones. At this point, we don't have the power to go beyond, and it's again a technical power. It has nothing to do with physics. We understand the physics very well. We know where it comes from. We know that it comes from the bubbling. We know very well the ingredients. We don't understand. Technically, we just cannot do it. If we had an infinite computer with an infinite power and an infinite number of students and postdocs, we could do it, with no problem, even with a large number. But it's just very hard technically. Doing numerics is very, very difficult. So the point is the physics. So in a sense, the singularity appears to get resolved all the way to here, which is again what we want in order for quantum mechanics to be happy with general relativity. And then of course you can take the electron away, and then you can get to the Schwarzschild solution. But I guess most of you know the black holes in the universe, they are not neutral. Do you know that? The sun is not neutral. Do you know that? Why is that? The sun is a plasma. When you have a plasma, you have electrons and you have protons. Electrons are very light. So when you have a plasma, you have a thermal distribution. The thermal distribution has a tail which has velocities which are bigger than the escape velocity. So when you have, for example, on the Earth, why don't you have any hydrogen? Because the hydrogen is very light. At the temperature of the Earth, the thermal distribution of the hydrogen has a tail which is bigger than the escape velocity. So the hydrogens keep on escaping, and over the history of the Earth, all the hydrogen has escaped. We don't have any more hydrogen on the Earth. We have nitrogen and oxygen, because nitrogen and oxygen have a tail which is very, very suppressed, and there are very few molecules which are outside, which have a speed which is bigger than the escape velocity, and therefore those molecules, very few molecules escape. Now, on the Sun, the same thing happens with the electrons. The electrons, because they are very, very light, they have a thermal distribution which is much wider than for protons. And therefore, electrons are going to escape much more likely than protons. And therefore, the Sun, if you just let it go, it will become electrically charged with a positive charge. Now, at some point, the process stops, because besides gravitational attraction, we also have electrical attraction. So the Sun actually has a charge such that it doesn't lose electrons anymore. And you can actually calculate how much charge the Sun has. But the Sun is charged actually. It's not a zero charge object. Again, because electrons escape. Because they're much lighter, so in the thermal distribution there are many, many more which have more than the escape velocity. So they just move away. So in the same way, when you have a black hole in the universe, all the stars have this. So the black holes which you find in the universe, because they come from collapsing stars, most likely they'll have some leftover charge. But even if they don't, so this will be the most likely Penrose diagram you'll get without any rotation. Now, this anti-brane story, what I told you, the way that you have supersymmetric solutions and you lift them with anti-branes, that's exactly the same as what people do when they do string cosmology. So in string theory is in 10 dimensions. People want to do our universe. Our universe is in 4 dimensions, and they sit there. So what do? They build string theory and they compactify it on some Calabi-Yau manifolds which have fluxes. There's a huge number of Calabi-Yau manifolds, and these Calabi-Yau manifolds are some ugly geometries which have topology, which have a non-trivial topology. And then what people do, they actually put fluxes on these Calabi-Yau manifolds. And again, there's flux going on this red circle, there's another one going on the green one. There are fluxes which people put on the Calabi-Yau manifolds, and they get 10 to the power 500 vacua. This is the usual string landscape. Everybody says string theory has 10 to the power 500 vacua. They come because you have a Calabi-Yau and you put all sorts of fluxes on this vacua. But all these fluxes are actually anti-de Sitter. They have a negative cosmological constant. Now, Mr. Universe in which you live has a positive cosmological constant. Hasta la vista. Don't ask me why, but that's what people measure. I wish it wasn't the case, but we have to live with that. So then the question is, what do you do with that? Now, people who want to build a sitter in string theory, what they do, they bring an ingredient which is an anti-D brane. They put it down some very, very long throat, and this anti-D brane actually uplifts the cosmological constant and gets you from having an anti-de Sitter to having a de Sitter. What we are doing for and this is called the landscape. This is the landscape. That's how the landscape is built. That's how the de Sitter landscape is built. Now, and again, people have all these arguments that the landscape, and we live in a multiverse. There are many, many universes with all the possible laws and all the possible things, and we're everywhere. And there's whatever fine tuning we find can be explained by this landscape. I'm not going to get into this anthropic argument, but we're supposed to be somewhere in this mess. However, in microstate geometries, we are doing exactly the same thing. We are basically saying I have a supersymmetric black hole, and I'm putting an anti-D brane, and I'm uplifting the energy to get a non-extremal black hole. It's exactly the same story. In terms of D branes and in terms of the physics is really one-to-one. It's shocking. It's shocking how close the two things are. Even if they're different parts of physics, one has to deal with the universe and how many universes you have and so on. The other one has to deal with the black holes and all the possible microstates of the black holes. The ingredients are the same. You have a supersymmetric solution, and the anti-brane uplifts it to positive cosmological constant of the Sitter, or you have a supersymmetric solution and you get more mass than charge. However, life is not that simple, because for the Sitter, what we have been showing in Saclay over the past many, many years is that antibranes, when you put an antibrane in the system, there are tachyons and there are instabilities. And essentially, if you want to build a de Sitter solution in string theory, you actually get instabilities, the system moves around, starts moving into many other vacua, starts decaying. There's a very messy dynamics. And for de Sitter, this is bad, because again, our universe is supposed to be stable, more or less. I don't clap my hands and I collapse the Andromeda galaxy. But for black hole microstates, on the other hand, this is in a sense a feature. It's not a bug, because when you have a black hole microstate, in a black hole microstates, things are very dynamic. There are many. So the fact that you are unstable, and again, the instability, where does it come from? It comes because you have this mode down at the jaw, and essentially the jaw wants to become longer and longer and longer. There's a mode in which really destabilizes this this compactification. So what's happening for the landscape is very bad. Essentially, when you have an instability, instabilities tell you that this landscape is invalid. The string cosmologists have to go back to the drawing board. They have to start calculating again. It's very bad for the whole field of string cosmology. But for microstates, it implies something very, very weird. It implies that microstates have a huge phase space. Near every microstate, there are n1 and 5 possible directions where you can go. And many of those are tachyonic. So somehow the black hole, the way the black hole functions, you have these microstates, which you build. And then the system goes into one, but then immediately goes into the other, and immediately goes into the other, and immediately goes into the other, and just hops around in this landscape, in this huge phase space of huge dimensionality, and completely messes up things. This is how the black hole. This is how the black hole is supposed to look like. This is somehow how the dynamics happens. You have these huge microstates which are horizon size, but they're not stable. They are top of the hill. They have instabilities, and one of them goes into another one, and then it goes into another one, and it goes into another one, and they keep on going, and they keep on mixing, and they keep on having this horrible mess. That's basically what this implies. We got to this picture by doing supersymmetric ones. The supersymmetric ones are frozen. So the thing is, if you want to understand this, it's like you have ice. You build ice is frozen, and then you decrease a bit the temperature, and you let some of the ice become water. When you get some of the ice become water, you see a bit of water here, a bit of water there, not too much. But if you let all the ice become water, then you get a lake, and then on the lake you have waves, and you have nonlinear dynamics, and you have all the stuff, all the molecules going around. But again, to get to this picture, you have to do ice first. Ice, we understand how the frozen system works, and that's what I try to explain you. And now we can relax, and we can try to go towards the non-supersymmetric system. And this is how it looks like. Again, it's a huge system with a huge phase space with a very non-trivial messy dynamics. Now, essentially, to conclude the part about supersymmetric and black holes, there are 4 different directions of research which tell me that something must be happening at the black hole horizon. The first one comes from information theory arguments, which people have been done, and essentially they claim that in order for quantum mechanics and GR to be reconciled, there must be something at the horizon, which is called a firewall or a fuzzball or something, but there must be some structure. This is about all theories of quantum gravity, nothing to do with string theory, nothing to do whatever theory of quantum gravity you find now, or you'll find 100 years from now, or 1,000 years from now, it will have to do this, because if you want to reconcile the two theories, something must be happening at the horizon. There's the same from ADS-CFT. You can argue that in ADS-CFT there should be some fields which have non-trivial waves, and therefore there should be have no spherical symmetry, and there should be no horizon. And that's again something which has nothing to do with string theory. ADS-CFT is something which could be established by itself as a correspondence between CFTs with operators of large scaling dimensions. It's something which in principle doesn't need string theory to work. It's something which can work independent of whether string theory describes the real world or not. Now, and again, those who are agnostic about the theory, but they also have no mechanism of how to get the structure. They just say something must be there, but again, they rely on pixie dust to keep the structure. If you want to build a structure, you have to either follow microstates, again, from the Stroman-Javafa regime all the way to the strong coupling regime. I didn't get a chance to talk to you. Or you can actually build this huge amount of geometries. You can actually just build huge amount of bubbling solutions, which is what we have been trying to do. Those are basically the 2 ways to build them up. Essentially, this is top down. You work in string theory and you build the guys. This is coming from information theory and effective theories, and it's saying something must be there. But the 2 things have not met yet. We know that something must be there. We have built it in string theory in a few examples, but we haven't made the junction between these things. So all these 4 things are pointing in this direction, but we haven't really understood the final picture. We just see 4 roots which converge to the same place. Now, a few questions. First of all, I've been trying to show that you have classical solutions. What I've been building, all the things which I've been building, all the superstrata and all the bubbling solutions, that are classical. However, things that are not maybe they're not classical, one can actually have a very complicated quantum dynamics. What one has to do, again, as a physicist, you have to do things which you can calculate. Classical solutions can be calculated with pain, but it's something where you can do calculation and you can trust it. Once you lose control, everything becomes quantum. You have no idea what you're doing. You cannot do any calculation. So it's very important to keep the classical solutions as again the building blocks, and just to give you an intuition of how things work. I'm not going to go through this. And then there's another question, which is, can you fall to the black hole horizon eating or drinking your coffee? As I told you, the black hole horizon is supposed to be this huge area, and the curvature is supposed to be very small. You can just go through there without any problem. Or are you going to go splat when you hit the horizon scale? And again, you can ask these questions by looking at cooked up configurations which have nothing to do with string theory, or which are not built up from a top-down theory, or you can actually use actual solution of string theory. But so far, the solutions which we have built, if you hit them, you are going to crash. That seems to be the story. Now, the big question which we discussed before, and I have 15 more minutes, and I'll leave a bit of time for questions as well, is the questions: how can you measure this? How can you observe these configurations? And to quote my favorite American president, there's a huge amount of new degrees of freedom at the horizon. These systems, again, because they have these bubbles, they really have a huge amount of degrees of freedom, stuff happening there. And the stuff happening there, these degrees of freedom at the horizon, they must be doing something. So again, when you have LIGO, when you have LIGO, sorry, not LISA, LIGO. I mean, when you have LISA or LIGO measuring two black holes, what we are claiming is that these black holes are not going to be nice and black. They're going to contain this huge mess of very dynamical bubbles moving around and collapsing and hitting each other and interacting. And you have a huge mess in one black hole, you have a huge mess in the other black hole. When the two guys merge, this is something at the scale of the horizon. Maybe there's something visible. Maybe I can measure something. Maybe the structure of the horizon could be measured. And there are basically three possible directions where I see something which could be giving a signal. Again, the structure of the horizon, which again I've been trying to show you how to build it, and I've been trying to show you how to understand this physics. There are three possible routes to understand whether the structure at the horizon could be measurable or not. And I'm labeling them as horizon viscosity, microstate mountains, and distortions of the Kerr multiple moments. Warning. This becomes speculation. This is speculative. I'm getting out of the realm of supersymmetric things where I'm very heavy and solid. If you ask me questions, I can answer you 100%. I know what's going on. From this on, it's, we're in speculation land. But again, they're experimentalists. They're doing experiments. We have to do something. We have to think. We have to think ahead. Even if I cannot build these solutions, even if I cannot construct Schwarzschild microstates, I have to try to use what I know for supersymmetric solutions to go towards Schwarzschild, to try to give something to experimentalists. And thing number one, horizon viscosity. What are we saying? We have a horizon. At the horizon, we have these big bubbles, huge amounts of degrees of freedom, the superstrata, functions of arbitrary shape, moving around, going into each other, fluctuating, and so on and so forth. Those are a huge amount of degrees of freedom. And you can ask how many degrees of freedom do you have in, for example, in a supersymmetric D1D5 system. The number of degrees of freedom is n1 times n5. That's a large number. And if you look at the black hole, write the black hole mass in Planck units, and square it. That's how many degrees of freedom you have. So again, the black hole mass is like solar mass, write it in Planck units to the power 2. That's a huge number of degrees of freedom, way more than what you have anywhere. When you have such a huge number of degrees of freedom, they can actually cause dissipation. For example, when you have an electron moving next to an electric plate, there's an image charge, and because you have so many degrees of freedom, they just steal your energy. They want to take your energy away. And this, if you distort the structure of the horizon, for example, if you put a bump on the horizon, or if you want to look at the ring down of a black hole merger, which people study in LIGO, this ring down, the energy in this ring down, because you have so many degrees of freedom, they're going to steal all your energy immediately, and they're going to thermalize you immediately. And essentially, these degrees of freedom, again, they're just going to eat up whatever energy you give them. They're just going to take it and go away with it. They're going to go away with it and dissipate it into this huge phase space. So essentially, it's very hard to get any reflection. For example, people have tried to get a reflection at the black hole horizon using this structure because, again, reflecting means you throw some energy and the energy goes out. The energy doesn't get eaten up. But here you have so many degrees of freedom, and you have to convince them somehow not to get excited, which is very complicated. So in a sense, what we are claiming is that the structure, because it has so many degrees of freedom, everything which falls into it gets eaten up. Now, I have a devil's advocate point. What are we trying to do? We're trying to find if there's a signal experimentally which distinguishes this big blob of mass with absorbing boundary conditions from the black hole. But the black hole already has perfect absorbing boundary conditions. The black hole in GR already eats up everything. So then the question is, what's the difference between the black hole which eats up everything and this thing which looks like a black hole which also eats up everything? Maybe there's no difference. Maybe experimentally there'll be no way to distinguish between them because both of them have this feature. Except that for the black hole, the way the black hole eats you is that you go into it, you cross the horizon, you cannot get out. The way this guy eats you, you go into it, you have n1 and 5 possible degrees of freedom. They all steal your energy and they go in different directions in the phase space, and you die. That's the difference. But as far as the dynamics is concerned, the net effect is the same. The energy gets eaten up and thrown into this. Whatever you throw in gets dissolved and thrown into this thing. So devil's advocate in this horizon viscosity. Yes, there are degrees of freedom. Yes, there's viscosity, but maybe the original black hole solution captures everything. Why do people get reflection and echoes? The reason is there are many people who actually compute the wave equation in the system and they get an echo, which makes sense. You have one geometry which is a throat and has a cap. If you solve the wave equation, first state, second state, third state, you can solve the wave equation very easily, and you can actually find the spectrum is gapped, and you can find that if you throw in a wave, you get a reflection. But this is assuming that the geometry is frozen. But we know that the geometry is not frozen. The geometry, all these black holes, there's a huge amount of phase space. All the geometries we are building are like points in a phase space. But you can go from one point to the other without costing any energy. That's what all these n1 and 5 degrees of freedom, they take you to nearby points in this huge phase space. So if you ignore these degrees of freedom, of course you'll get reflection. Your energy is going to come out. But physically, you cannot ignore them because you have them there. So people get reflection because again, they're looking at one of these guys, ignoring the huge phase space of them and ignoring their interaction. So this is one thing, and I think there are people who do gravity waves and they look for reflection. They put reflection with a coefficient, but I think based on my understanding, I don't think the reflection will be there. There are people who argue against me, but that's what I believe. The second question is, what about microstate mountains? What's a microstate mountain? I told you that you have these microstate geometries, and they are not spherically symmetric. The black hole is spherically symmetric, but every microstate is different, and some of the microstates may have some spherical eccentricities. They may not look exactly like they may not have a perfect translational invariance, and therefore, let's say you have two black holes, one black hole here, one black hole here, and this black hole has a tiny mountain on top of it. Because again, it's a microstate and the microstate has a mountain. When the second black hole goes around, it actually sees a different metric. And therefore, there will be a non-trivial jitter on the incoming black hole. The black hole, as it moves around, it will not feel a spherical symmetry. It will actually feel a tiny bump every time it goes around, and it's going to have a different signal. So it's possible that when you have these microstate mountains, when you have two black holes merging into each other, there will be a non-trivial noise which appears, which the classical black hole solution doesn't. The classical black hole solution is nice and spherically symmetric. Now the question is, how big are the mountains, how wide are they, and how tall are they? If you know those numbers, and again, we don't know them because we don't have structured solutions, if we knew these numbers, we could be calculating, as the signal. Devil's advocate, maybe typical microstates are going to be very spherical, maybe these mountains are going to be Planck size, and therefore it will be impossible to measure them. It can happen, but again, that's what we are doing. We're trying to understand all the options. Moreover, there's another way in which you can measure these things. If you look at a spinning black hole, if you look at a spinning Kerr black hole, the spinning Kerr black hole has a dipole moment, but also has a quadrupole moment, octupole moment, 16-pole moment, and so on. It has all these dipole moments. If you look, instead of looking at a spinning black hole, if you look at a spinning shell of dust, or at a spinning liquid, or at a spinning solid shell, or at a spinning anything, the dipole moment, if you have the same dipole moment and the same mass and charge, you'll have different quadrupole moments, octupole moments, and so on. Because if you spin a ball, you get one result. If you spin a glass of water, if you spin a shell of water, you get a shell of metal, you get another result. If you spin if you spin water, you get another result. Every object, every stress energy, so given a stress energy tensor, you can actually spin your configuration and you get different results. People who do neutron stars have this very well taken care of, because people who do neutron stars, they have different equations of motion, and the equation of motion of the neutron star determine how the neutron star is tilted and how the multiple moments are. And in principle, if you do gravity waves with something called MRIs, extremal mass charge, when you have a big black hole and a small black hole which moves around, in principle, those gravity wave infalls, which could be measured by LISA, in principle, they can distinguish up to a large number of multipoles. And using those, you could actually find exactly whether you have a curved black hole, or whether you have a spinning shell of dust, or whether you have a spinning ball of metal, or what you have. One can actually test very well the GR and the black hole paradigm using this extremal mass ratio in spirals, which again should be measurable by LISA whenever LISA was going to fly, which will happen at some point. We don't know yet. We don't know whether we'll still be alive when it will happen, but it will happen at some point. So our future generations, using our results may actually get some nice physics. What we need for that, in order to understand what are the distortions of the dipole moments, you need to build Kerr microstate geometries. We don't have them, but what we have microstate geometries for a region of the Kerr black hole, which is called the near horizon extremal Kerr. And what one has to do is to glue it to Kerr to find what these numbers are. But that's something which we're trying to do. I'm going to. The problem is, there's some other arguments which go under the name of fastball complementarity, showing that even if you build this stuff, whatever stuff makes the black hole, whatever stuff makes the microstates, it will have the same dipole moments as the black hole. Maybe, it may happen. And in that case, even if we do all these results, we're going to get the same result as the black hole. That's the bad case scenario. But again, we have to be open-minded. So, just to summarize, and then we have some time, what I try to show is that in string theory one can build configurations which can hover above the horizon. It's a very non-trivial mechanism. It involves, three things: enhanced quantum tunneling, growing with gravity becomes stronger, and having a support mechanism. All these three things are present in string theory and involve, non-perturbative degrees of freedom. If one can do them in other theories, head down, it would be really great. Moreover, I try to explain you how to get supersymmetric black hole microstate solutions using, bubbles with fluxes. I showed you why the bubbles with fluxes don't collapse, what keeps them there. And I showed that we can get these superstratum solutions which have, huge amount of, there are huge amounts of families. And hopefully to extremely non-supersymmetric black holes one can extend all this game. And the question is, how do you extend it to non-extremal black holes? It should, because that's what information theory, firewall, fastball arguments show. It's near extremal, maybe it works. Far from extremal, it's very hard, and we don't know. And we are really into terra incognita when it comes to experimental consequences. Thank you. And I have to sit down. Sorry. Okay, questions?
So you mentioned how these instabilities could sort of be interpreted in terms of Hawking radiation. Can you estimate the lifetime of these objects or not?
For extremal black holes,
for extremal black holes, of course, they don't radiate.
Yes. If you do near extremal, Hawking radiation is very weird. That's something which is a project which I had in mind ever since I was a postdoc, but I never sat down to do it because near extremal black holes have a very weird Hawking radiation. It's really suppressed exponentially. And moreover, what gets Hawking radiated is more often the charge. When you have a near extremal black hole, instead of the near extremal black hole says, I can dump my non-externality to become extremal, but it's much better off if I dump my charge, if I spit out my charge, and I actually become more non-extremal. And it's actually so there it's a bit of so in a sense the near extremal black holes have actually two kind of instability channels. One of them is, let's say, classical Hawking radiation, where the non-extremal black hole dumps up the energy and becomes extremal. But the other one is actually where it dumps up the charge and actually becomes more non-extremal. and with the lower mass. So that's something which we're actually studying. We have a project going on right now. So it's a very good question, but I have no. I mean, it's complicated for near-extremal black holes. It's not as simple as for extremal ones. As for non-extremal ones. More questions? Yes.
Maybe the
Fire.
second thing we discussed, like you have these very nice, in principle, constructions you can do that have all these nice properties. How realistic would it be, even numerically, to like dynamically generate them from some sort of collapsing matter model or whatever? Like show that these actually numerically false.
Yes. So for me, the main thing, I mean, if I had a numerical, I mean, we're having a numerical postdoc in Saclay right now, so I hope he doesn't watch this thing, but. And tried in the past. Numerically, what could be done? If one can actually build a huge number of solutions which are cohomogeneity 2 and have bubbles, then if one uses them, you can actually understand using them what are the instabilities, what are the decay times, whether they are typical or not. They are still not going to be the more generic ones, but you can understand from their decay times and from the way they look and from the physics they have, you can understand from that whether they can actually match typical states or not, and whether they can have enough entropy nearby them to give it the black hole entropy. That's my hope. Now, to do bubbles of cohomogeneity 2 is very complicated. People who do numerics, what they do, they have something called the pentagon problem. So essentially they have something called the rod diagram. When you have a black hole or when you have a bubbling solution, there's something called the rod diagram. So a solution depends on two variables, and there are two angles. One angle shrinks at some location, the other angle shrinks at the other location. So if you have to draw all the lines where the angles shrink, and then you have to basically find some coordinates which map this thing very nicely. And then the problem can be mapped to a problem of second order partial coupled differential equations in a pentagon. A square is easy because you put boundary conditions and you solve it. It's very easy to solve. A pentagon is more nasty because a pentagon is like a square without a corner. And then if you want to do more bubbles, if you want to do, for example, 3 or 4 bubbles, you need to get a hexagon, heptagon, and it's becoming painful numerically. But there are people who can do it. There are people on the planet who do pentagons and hexagons and heptagons for other applications, for ADS condensed matter, for holography. I mean, there are people who do those things. So in a sense, we are not, the degrees of freedom are out there. Now, at my age, it's quite unlikely that I'll start picking up these methods and, before I retire, learn how to do these things and so on. Because again, to get to the level of expertise, one needs a few years. It's much more likely that, if we find somebody from that group who works with us, we can actually build these solutions. Once we build these solutions, we'll understand very well, again, what are the decay times, how fast they thermalize, how fast they scramble, all these thermodynamic questions we can understand, and then we can understand whether we have the typical things or not. And maybe once we build them, we say maybe they don't do what we want. Maybe the thing will fall down. Maybe one cannot build them. It's also possible. And at this point, we haven't been able to build numerically even one of those things. So I don't know whether they exist. Maybe they don't exist. Maybe there's some deep reason, and God is not happy with us, and maybe the whole thing is going to crash. I have no idea. But we have to try. That's my vision. Based on the extremal scaffolding, that's the next level to which I want to build. But I have no idea whether it will work or not. I hope it works. And again, until now, we've been actually, just to give you a story. So there's this saying in Alice in the Wonderland that somebody says, this is an impossible thing. And I think it's I think it's the cat, the Cheshire cat, who says something like, yeah, I like to do impossible things. In some days, I want to do 7 impossible things before breakfast. And somehow what's been happening for these microstate geometries is that they were supposed to be undoable. There are theorems that they're not supposed to exist. There are all these places, and we've been working on them for 15 years, and every once in a while we bumped into a place and it looks like the whole thing got stuck. There was a theorem saying that some spaces don't exist, mathematical theorem, math guys proving it and so on. There was some other place where again some solution was going to be singular. We could never get it to be smooth, and we kept on pushing using string theory input. And every time when something looked impossible, we were always able to get over it. And it happened really like 6 or 7 times. So it's really like in the Alice in the Wonderland, 7 impossible things before breakfast. So until now, all the times when we could have gotten stuck, and there were reasons to get stuck, again, based on physics, based on math, based on everything, somehow, we were lucky and things went. Now maybe the 8th time will collapse and will crash and will die. I don't know. But until now, we've been lucky 7 times. I have good hopes. That's. You guys are tired. I guess it's past 10 o'clock.
So how happy are you with this negative mass objects?
Sorry?
How happy are you?
I'm very happy. I'm a string theorist. String theory has negative mass objects. They are called orientifolds. They are very weird objects which appear as boundary conditions. So for example, if you do compactification of string theory to 4 dimensions, you get some charges. But in a Calabi-Yau manifold, the charge has to be 0. So you get some charges in some regions where the standard model lives, for example. You need to put some d-branes and some charges. And then the charge has to be 0. So you must have negative charge object. If you don't have such object, you can never get any real world compactification of string theory. And these orientifolds, again, if you look at them as gravity objects, they are horrible, negative mass, negative charge, you shoot yourself. But if you do string theory on them, they actually become nice and beautiful. And they really have all the right physics there, and essentially they are good ingredients. But as a gravity person, of course, you should be throwing them away to the garbage. But string theory comes and tells me, no, hey, wait a second, don't throw them to the garbage because, they are nice objects, they make sense physically in string theory, so one has to use them. That's basically the story. And there's one example of a negative mass object in string theory which actually becomes a nice solution of general relativity, which is something called Atiyah-Hitchin space. So there are 4-dimensional hyperkähler spaces, and one of them is, again, this Gibbons-Hawking space I told you about. It has a V which looks like 1 plus 1 over r. 1 plus 1 over r, the 1 over r, this has charge 1. But there are some solutions called Atiyah-Hitchin, and if you look at infinity, V looks like 1 minus 1 over r. And this implies that this Atiyah-Hitchin space, if you compactify to type 2 string theory, it has a negative d6 charge and negative d6 mass. But in 11 dimensions in M theory, it's a perfectly nice, beautiful geometry. But it just happens that when you compactify it in string theory, it looks like this negative mass, negative charge object. So we have examples of solutions which are nice, beautiful, but somehow. So string theory tells me this guy should exist, and this Atiyah-Hitchin space, which was found long before people understood this, has this feature. So in a sense, these negative charge objects and negative mass objects, they come in, through in compactifications in this Atiyah-Hitchin space. They come in all these examples. So we have to take them into account. Okay, let's call it a day. Thanks a lot for the.